Yes. So once again, hello everyone. I'm very glad to welcome you in Moscow State University in our department, chemistry department, and specifically our division of radiochemistry, where we are located now. And we just counted, this is our sixth school, international school on radiochemistry. It is our third school, summer school, and later this year will be next winter school, also on radiochemistry. And this is our second school on the decommissioning, so the people who already participated will notice that some topics are really similar to the previous one, but also there will be some new lecturers, new topics covered by our specialists from Company 12 and institutes of Rosatom and international experts from IA and other organizations. So I believe that it will be very useful for all of you and also for us, because me specifically, I'm a radiochemist, so I'm chemist in my specialty, and for me it will be very nice to listen some specific topics in decommissioning, some technical stuffs, and etc. So my name is Vladimir Petrov. Sorry, I didn't introduce myself. I am an associate professor in this radiochemistry division. And during this school, you will be guided also by my colleagues, Andrei Putyatin, by Olga. Olga, where's Olga? Not here. Okay, Olga Yakubova and our assistants like Timofey or Tima. How is better? Tima. Okay, so Olga Yakubova, Tima Putyatin, and Yulia Guzhonkova. Just Yulia, I think it will be easy. Yeah. So just a few, few formal words. We will have lunches as usual, not here, but in other building at the Department of Chemistry. So at the main building of the Department of Chemistry, and my colleagues they will guide you to this building. So at least, yeah.
A little bit sophisticated procedure of registration, and of course I will escort you to the chemistry department, but please always have your badges with you. At the entrance you will have to show it up, right? And the person at the security there will check, are you with an analyst? Of course you are, in both in Russian and English, whatever, right? But this is, just not to be forgot. You should have your badge on a regular basis. Secondly, we will have, we will advise you later a little bit what are the procedures. So in fact, your lab is covered with your grant, but there are some limitations, but we will, describe it a bit later. Okay?
Okay, thank you. Also on the Saturday, it will be a tour in Moscow. We will organize it a bit later, the specific schedule. Yeah. Tomorrow and the day after tomorrow, it will be practical exercises. Tomorrow it will be exercise in laboratory, and on Wednesday it will be just a theoretical exercise, let's say. And on our last day, it will be some specific exercise. We will, like a game, we will try to figure out how you accumulated the knowledge, let's say. It will be some specific tasks about specific objects, and we will divide you on 4 or 5 groups, and we will ask you to solve the problem in 1 hour. So it just like really a game. You will make your suggestions, so that there will be no correct answer or incorrect. It just like what are your thoughts about this problem. But it will be like a small surprise at the very last day. Today, as usual, we have some introductory test. And again, as for people who already participated in our school, some questions will be, I would say, familiar. But for other people, will be new, and for us it is important to understand the progress of the people from the very beginning of the school to the end of the school. And some more specific details about the restrooms. We have restrooms on the 2nd and the 1st floor, just on the right side of the staircase. We are located on the 3rd floor, so the 2nd and 1st floor, you will find the restrooms. Andrei, you... Technical tour, yeah. Tech tour will be on next Tuesday. We will visit the facility called Radon. It is the radioactive waste management facility. So the specialist in the treatment, pre-treatment and conditioning of and storage of radioactive waste. So I guess it will be very interesting to see how it looks in real life. And yeah, we will start from hotel. At what time? Okay. Yeah, okay. And it will be the whole day there, and yeah, I guess it will be very exciting. What else I forgot to say?
So today we have
Yeah, we will have you mean dinner, or yeah, so the welcome reception will be today at a restaurant called Durdin. So it's a Russian restaurant, quite good. And our not final, but let's say a few days before our final dinner will be next Monday, but it will be in another place in the hotel, if I remember correctly. Maybe. Okay, so it will be also specified later. So again, I'm really glad to see all of you, maybe again, or the new persons. I really like to see so many people from different countries in our university. And so we will, maybe Andrei, would you like to say a few words? You can take this mic. Like this. Because yeah, if you will have questions, we will give you a mic, because there is translation to the Zoom, and so people will hear you via these mics.
So, dear guys, dear old friends, dear new friends. So I'm very glad to see all of you here in Moscow. So it's now it's not so hot, and I think it's very it will be very useful for you, I think. Yeah, thank you to Vladimir for preparation lecture part in this school.
Okay.
Yeah, thank you. So let's start.
One more thing that I forgot to mention. No, I have every day, please sign this list of the participants. It is formal things for our report that everybody, or most part of the participants, were here. So please. And now, as I mentioned, the traditional part of our school is the tests. So again, Here there are some correct answers, but don't be afraid. There is nothing to judge you. It is just for us. Там два, наверное. Two pages, yeah. No, it's another side. Yeah. Thank you. Thank you. So, what's this? Mhm. Mhm. So as we finish the test, now we can have a short coffee break just to relax, and then we will start with the lectures. So please take coffee, biscuits, just relax for some time. So, dear colleagues, we'll start in a minute. So we have two Wi-Fi nets here. I had written the names of the Wi-Fi nets, either 308, this is the room number of our auditory, or the net called Professor. In the first case, the password is public event, small cases, and for Professor, it's Radiochemistry. So, we just checked that the first net is not working very well right now. On Friday we have checked, but it was okay. But now it's some problems with this net. So you can use either Professor or 308 if it works with your device. Okay, so we'll start with the general lecture, let's say, about the decommissioning in nuclear fuel cycle in general, but not only in nuclear fuel cycle. We'll see it later. So why nuclear energy in general? Today we have in the world quite a lot of deficit, or quite a big deficit of energy around the world, not maybe in Russia or Europe, but in so-called developing countries. You can see that there are not so much energy, so it's a night map, and the photo was made by NASA from the International Space Station. And you can see that you can clearly see that some regions are very bright in this map, like Europe, USA, some East Asia, but many regions in Africa or in Central Asia or in Latin America, they still don't have, let's say, not energy at all, of course, but some deficit of energy they have. And according to the World Health Organization, around 2 million of deaths per year, they are due to the exposure to the indoor air pollution. Means that people are using organic fuels like charcoal or just woods or other organic materials to heat their homes, and this air pollution, indoor air pollution, causes this excess deaths. And due to the lack of the energy or energy poverty, around 1 billion people don't have sufficient health care. So that means that energy is needed not only for industry or for charging our devices, let's say, but also it is necessary to provide healthcare for people. The former IAEA director claimed that if we want to reach the climate change goals by 2050, we have to change the source of energy, electricity, by 80% to the low carbon sources. So low carbon sources, in general, we are thinking about the wind energy, about the solar energy, about hydro energy, but around these low carbon sources of energy, the atomic energy is one of the most safest and let's say most clean source of energy. There is a compilation of data about the death rate from the accidents and air pollution during the production of energy by different sources like coal, oil, natural gas, biomass, and these 4 low carbon sources like hydropower, nuclear energy, wind and solar production. And also comparison on the greenhouse gas emissions. And if this part, the greenhouse gas emission, is more or less clear for people, for public, everybody understands that solar energy or wind energy, they don't produce much CO2 or other greenhouse gases, and as well as the nuclear energy. Of course, they still produce some of them, because CO2 produces not only when you burn the coal or gas or oil, but also when you produce cement for building or for construction of the buildings or other facilities. Or you use cars or trucks to deliver your materials. So CO2 production is inevitable, so you always produce some CO2. But if we compare the amount of the produced greenhouse gases by these 4 sources of energy, they are much lower than if we compare with the coal, oil, or other sources. So this part is more or less clear for everybody. But if you ask people about deaths caused by the nuclear energy, I think that you will get very different answers. And I'm quite sure that if you will go outside and ask people on the streets how many people are died from the sources of the ionizing radiation, they will tell you like millions, or I don't know, 10,000s or 100,000s of people. But it's actually not true, because if we will see even the deaths from the caused by Chernobyl accidents, even the most conservative assumption says that it is not more than 4,000 people. It's not registered deaths. It's just assumptions, estimations, and the registered deaths are not more than 134, if I remember correctly. So this low number of deaths, and if we remember the Fukushima accident, there is 0 deaths by ionizing radiation. People died due to the flooding, mainly. And if we calculate all the deaths that are caused by accidents during the material production as well, like in coal mining, fortunately not every day, but several times per year we see the news in the media that in some mining there are accidents and some explosions of methane, or some other accidents in mines, and dozens of people died due to these accidents. So that means that the production of energy by coal or other sources like oil, they cause deaths not due to the CO2 production, let's say, but due to the accidents when the coal or oil produced or extracted from the earth. So, and if we calculate all these deaths from the accidents and divided by the amount of the energy produced by the source of energy, we will get this diagram, and you can see that the nuclear energy is one of the safest source of energy in the terms of the death rate from accidents. Also, nuclear energy is a very concentrated source of energy. I'm quite sure all of you are quite familiar with this, that energy produced by the nuclear sources around 100,000 times more concentrated, let's say, than coal or gas sources. And if we compare the amount of energy produced by this track of the gas, so 26 cubic meter, the same energy is produced by 26 milliliters of nuclear fuel. So more or less, if we also take into account the density of the gas and the nuclear fuel, so it will be approximately this relationship. So again, nuclear energy is very concentrated source of energy. That means that the square, that area that is needed for building the nuclear power plant or to produce the energy with the nuclear sources is much smaller than any other low carbon, or let's say low carbon source of energy. So there is a comparison between nuclear power plant with the 1,000 megawatt power production, and the same amount of energy will be produced with the wind or solar power plants with this area. So for solar energy, it is 75 times more in area, and for wind power plants, it's more than 300 times more land required to produce the same amount of energy. Yeah. Milliliters.
Yeah.
So if we take into account the mass of this gas with density and all these calculations, and we know how much energy is produced per 1 kilo of the gas, and if we calculate how much nuclear fuel we will need, so it will be around 26 milliliters. No, it's milliliters, because we take into account density. So yeah, we can compare the masses, but it's, let's say, more representative how concentrated the nuclear energy is. Yeah, it's milliliters, not milligrams. Yeah. Okay. So again, these 4 low carbon sources of energy, they form so-called green square, and we have 2, let's say, constant sources of energy that are not dependent on climate conditions or weather conditions, better to say. They produce the constant amount of energy during the time day, during the year. But these 2, wind energy and solar energy, can be like assistant sources of energy to make more energy in peak production, when more energy required during the day, when most of the people are working. So in together, these 4 kinds of energy sources can provide the constant production of the energy during the whole year and the whole day. And nuclear energy, again, can play a really valuable role in the provision of the energy. And nuclear energy, as we can see from the history of the nuclear energy, can do it safely. Of course, again, everybody remember about the accidents and nuclear power plants. But again, we have more than 400 nuclear reactors around the world, and at this time we know about, let's say, dozens of accidents from the whole history of the nuclear energy. So today I would say that nuclear energy is not absolutely safe. Of course, there is no absolute safety at all in our world. Even when we use, I don't know, elevator, it is not safe. But everybody use elevators or cars. Many people dies every day in car accidents, but still we are using it. Of course, there is no absolute safety in the world. And but still, nuclear energy, I would say, is one of the most safe sources of energy nowadays. And for us, as we are specialists in nuclear energy, in radiochemistry, in radioactive waste management or decommissioning, it is important to show people, to show the public that we can manage all the problems, all the materials, radioactive materials that are produced during the use of nuclear energy. We can manage all these problematic materials safely. And if we look on the nuclear energy, one of the main problems, it's not only the old buildings that are now exist in quite a large number, but also radioactive waste that are produced in any action when we are working with radioactive materials. And to understand what is radioactive waste and what is not, it is important to remember what is radioactive waste by definition. So the first part of definition is that it is materials that contain or contaminated by radionuclides, of course, because it is radioactive. Also, as far as it is waste, that means that there is no use with current technology. Of course, maybe in, I don't know, in 50 years, in 100 years, these materials can be used, but today there is no technology that can be applied to use these materials anymore. So that's why it is waste. And that is also very important that the concentrations, or let's say activities, as we are talking about the radioactive materials, should be greater than the clearance levels established by government, let's say, so by the regulatory authorities. So why it is important? Because again, I am sure you know that every materials, even we, contain radionuclides. Yeah, so when I die, my troop will contain still radionuclides, but it doesn't matter that I will be radioactive waste. Yeah? So there will no further use anymore, and that body will contain radionuclides, but it will be not considered as radioactive waste, I hope. Yeah. Because if we are looking on Marie Curie, for example, yeah, so yeah, it's another story. But in general, many materials that are around us, they contain radionuclides, of course, and even if it is waste, we don't think that they are radioactive waste, because the amount or concentration of radionuclides are quite low in these materials. So nuclear fuel cycle, when we are speaking with public, very often, if you are talking about the nuclear energy, people think only about the nuclear power plant. But in fact, there are many more steps in nuclear fuel cycle, not only the production of electricity in nuclear power plant. So it is started from uranium mining, extraction of uranium, refining it, production of the uranium hexafluoride, enrichment of uranium, then fabrication of nuclear fuel. Only after this, we use it in nuclear power plant to produce electricity, and then we stored the spent nuclear fuel in pools for cooling, and we wait several years for further treatment of the spent nuclear fuel. And then, if we don't recycle the materials from the spent nuclear fuel, we dispose it directly to the repositories. So in this case, it is called open nuclear fuel cycle, and the open nuclear fuel cycle is applied in Sweden, in Finland, in USA, more or less, and other countries. Or if we extract the valuable components from the spent nuclear fuel, so the fissile materials like uranium and plutonium, so we can use them again to produce the MOX fuel, for example, or the new type of fuel, nitride fuel, mixed uranium-plutonium nitride fuel. So we produce the fresh fuel from these recycled materials. Then it is closed nuclear fuel cycle. And if we will look at every stage of this nuclear fuel cycle, for example, starting from mining, we can use different ways of mining depending on the geological conditions for the specific ore. We can use either carriers or mines or underground leaching. Still, we will have these tailings, and these tailings, they are considered as radioactive waste, because in these tailings we have naturally occurring radionuclides, but at very high concentrations. So we concentrate natural radionuclides. When people say natural, very often they think that natural is good. Yeah, so why we should be aware of natural radionuclides, because it's nature, it's our home. But no, when it is concentrated, they possess quite a lot of hazard, and we should manage all these tailings in a proper way. So starting even from the first step, from the mining, we already produce quite a lot of radioactive waste, and the areas contaminated with these radionuclides. Then there is extraction and conversion of the uranium to uranium hexafluoride, and again we have quite a lot of buildings and areas where we stored the uranium hexafluoride, and the territories around the buildings very often contaminated with high amounts or high concentration of uranium. It is also the case when we enrich uranium. So for enrichment, we can use either gas diffusion methods or gas centrifuges. In Russia, we use mainly gas centrifuges now, not gas diffusion as in the past. And you can think that, okay, here we use the solid uranium hexafluoride that is evaporated and uses as a gas in these devices, so there should be no leakage, but that's not true. Also, you can see that these huge buildings, hundreds meters in long, and all this equipment, they're working with use of oils, with smaska, lubricants, and there is always leakage of these materials. And year by year, the territory around these buildings is also contaminated with uranium. Then there is a production of the nuclear fuel, and again, it seems that we have uranium hexafluoride. We convert it to uranium dioxide, for example, or if we have a mixed uranium-plutonium fuel, we convert it to MOX fuel, mixed uranium plutonium oxide fuel. Anyway, it is solid materials. There should be no contamination with solid materials in general. But during the production, there are quite a lot of fuel, not a lot of course, it's some fractions of percents with the defects or some old fuel. So defects means it can be mechanical defects or inhomogeneity in the distribution of the components of the fuel. So anyway, this defected fuel should be refabricated. That means we dissolve it and we produce the new fuel. During these processes, we produce quite a lot of liquid radioactive waste. Again, so every step you can see that we produce either contaminated territory or we produce radioactive waste. Nuclear power plant. Here, the nuclear fuel is transported in a very stable form, and there should be no leakage, of course, and there are no leakages in principle. But when nuclear power plant is working, some materials like ion exchange resins are used to purify water from the produced radionuclides. And these ion exchange resins now represent radioactive waste again. So even at nuclear power plant, where people think that there are no release of the radioactive materials, we still produce a lot of nuclear radioactive waste in the form of, for example, ion exchange resins. Then, when the nuclear fuel worked in the nuclear reactor, so there are a lot of new materials produced inside the fuel. So if it was in the beginning just uranium oxide, but after a few months, we see the production of many other elements. So this fission products, not only fission products, but also activation products, plutonium, for example, or neptunium, americium, curium inside the nuclear fuel. And all these elements, they have quite different chemical behavior, of course. Some of them form metallic particles, so-called epsilon phase or epsilon particles. Some of them form salt, some of them gaseous. So it's a really complex material with different properties, that differ from the initial material. And of course, due to these changes, the properties, mechanical properties, teplophysical properties are changed, and nuclear fuel stopped working at some point. And we should change, or we should take the spent fuel from the reactor and put the fresh fuel. This spent fuel actually contains quite a lot of fissile materials like uranium and generated plutonium that can be used again. So around 97% can be used again, and only 3% are fission products that cannot be used anymore. But they cannot be used in nuclear energy, but they can be used in other applications. For example, strontium-90 can be used for thermal generators, thermal electric generators. Cesium-137 can be used as a source of gamma quanta, and some other applications. So even from this 3%, some materials can be used again. But yeah, again, if we don't recycle, it is open nuclear fuel cycle, and we dispose our spent nuclear fuel directly without any reprocessing, or we can extract or separate valuable components. And in this case, we are talking about the closed nuclear fuel cycle. Why also why we should reprocess spent nuclear fuel? What are other reasons? Here is the, I think, quite famous representation of the how long the radiotoxicity of the spent nuclear fuel exists with the time. So if we can take the natural uranium ore as a reference. So natural uranium ore is a, let's say, reference that shows us that we should reach the same radiotoxicity, or let's say activity in more simple words, to be sure that we bring the same activity to the ground as we take from the ground. So if we don't reprocess spent nuclear fuel, its total radiotoxicity will reach the level of natural uranium ore only after, let's say, 200,000 years or even 1 million years. So depends on the type of nuclear fuel, depends on the how long it worked in the reactor. But in general, so it's quite a long time. And we should provide the safety of the repository of for such a long period of time. It's quite difficult because, of course, we have mathematical models that can show us how different materials will behave with time and how geological conditions will change with time. But if we will look in the history of the humankind, it is only around 100,000 years of the human exist. And we should confirm that our building will be stable for such a period of time. Yeah, prediction is possible, but who knows in reality. But if we extract the long-lived radionuclides from the spent nuclear fuel, then we can reach the level of the natural uranium ore in just 300 years or maybe 1,000 years. But this period of times is already known for our history. We know buildings that are stable for this period of times, made of cement or other materials. So we can really say from the experience, people's experience, that we can build the buildings that will be stable for this period of time. And in this case, we can say that the safety of this repository will be confirmed. So this is another reasons why we should reprocess spent nuclear fuel to reach this equivalent to the natural uranium ore in a shorter period of time when without reprocessing. But the question that can arise that if we remove the long-lived radionuclides, it doesn't mean that we destroy them. We just put them from the spent nuclear fuel to another place. So that means that we should store them again for this long period of time. But to solve this problem, there is a solution in building of nuclear reactors of new generation, the fast neutron reactors, that can burn these long-lived actinides like americium and neptunium. Curium has not very long period, not very long half-life, so it's only 18 years, and we can store it. It will convert it to plutonium, and we can use this plutonium either for practical application or as a part of fuel. So anyway, these actinides can be burned or transmuted to the short-lived radionuclides in the fast neutron reactors. Also, such a long-lived radionuclides as technetium and iodine can be also transmuted in the fast neutron reactors, even to the stable nuclides. For example, technetium can be converted to ruthenium that is stable. So that is, I believe, our future, to separate the long-lived radionuclides and convert them to the short-lived or even stable nuclides. Also, when we reprocess spent nuclear fuel, the amount or the volume of the high-level waste is very small. So this is a comparison of the volume of the high-level waste generated by using the nuclear energy by one family. So it means 4 members in a lifetime of 70-75 years. And it is very small. It is much smaller than the conventional garbage that we produce every day, I think. And if we reprocess the spent nuclear fuel with the extraction and transmutation of the long-lived radionuclides, the volume of this high-level waste will be even smaller. So the reprocessing of spent nuclear fuel is can be very efficient from the many sides. For example, again, it is reuse of the fissile materials. It is decrease of the time of the potential danger or potential toxicity of the radioactive materials, and it is decrease in the volume of the high-level waste generated by nuclear energy. To separate the elements, we use mainly the liquid extraction. One of the main process in the reprocessing of the spent nuclear fuel, it is so-called Purex process. We will not go in details. It will be another lecture in the schedule. Just to show you that in reprocessing of spent nuclear fuel, we use organic materials like tributyl phosphate with paraffinic diluents. We are using acids, and so we produce a lot of liquid radioactive waste. And additionally to the Purex process, another new systems are developing under development for separation of other elements, separation of cesium, strontium, americium, curium, technetium, etc. So there are quite a lot of new systems that are under development, and that means that one of the purpose to develop all these systems is to decrease the volume of the liquid radioactive waste, to improve the efficiency of the separation. But anyway, we will produce this liquid radioactive waste when we are using solutions, either aqueous solutions or organic solutions. They're still liquid. And in the former time, not only in Soviet Union, but also in USA and other countries, all this liquid radioactive waste, they were stored, let's say, not in the proper way. Yeah, in Russia, it was just an open ponds. The intermediate level waste were disposed in these ponds. In USA, these tanks, cement tanks, they existed from the 60s years, and they are not repaired, and they started to leak. And we know in UK or in France, they dispose radioactive waste in the sea. So the liquid radioactive waste is really a problem. The concept of a new reprocessing plant in Russia says that there must be no liquid radioactive waste generated at all. So every liquid radioactive waste that are generated inside the plants should be treated, that outside of the plant we will have only solid blocks of the radioactive materials, no liquid radioactive waste. The main idea to dispose the radioactive waste, of course, after immobilization of the liquid radioactive waste, is so-called multi-barrier system. So first barrier is a solidified matrix of the radioactive waste. So it is either vitrified, so the glass matrix for high-level waste, or it can be cement matrix for intermediate or low-level waste, or some other materials suitable for specific types of radioactive waste. This matrix is placed in a canister made of durable material. It can be either stainless steel or even copper, like in the Swedish concept. And when we put this canister inside the geological media, there is a special buffer system and overpack system. And the buffer system, mainly it is clay materials, either bentonite or other clay materials, sometimes with sand, just to make it not so costly. So sand is very cheap material. So, but clay materials, their main properties is to stop the water penetration, so to stop the water flow towards the canister. And from other hand, the clay materials, they demonstrate quite a good sorption properties to the radionuclide. It means that even if the canister will collapse and damage the radionuclides that can be released from the matrix and from the canister, they will sorb on these clay materials or other buffer materials. And of course, the geological media itself is quite a good barrier for the radionuclide migration. So it's like a Russian doll, or as we call it, matryoshka. So many barriers around one central part. Yeah, so to prevent the radionuclide migration. The, let's say, good properties of radioactive waste, if we can say it, is that radioactive materials decay. Yeah, so the activity decreases with time. That means that the activity or dangerous of radioactive materials is finite. After some years, the hazard of radioactive materials will be negligible. We can compare it with other stable materials like lead or zinc or mercury, for example. Yeah, there are stable elements and they not decay, and they will possess a hazard for eternity. But radioactive materials, they decay, and so at some point their hazard will be negligible. So this is one of the good things when we are talking about the nuclear energy, that the waste from these sources of energy, they have a finite period of time when they are hazard. So again, where this radioactive waste materials, buildings, facilities are existed in nuclear fuel cycle everywhere. Yeah, at any point, if we are working with radioactive material, we certainly produce some radioactive waste, radioactive materials. We have contamination, and we have to deal with this. And if we are looking in the life cycle of any nuclear facility, we have, of course, planning, we have design. This means technical documentation, cost estimation. When we construct our facility, we operate it, so we have some benefits from the nuclear facility. Doesn't matter either it is production of energy or production of radionuclides or other benefits. And then the final stage of any nuclear facility is the decommissioning. And as we can see, that decommissioning should be planned at every beginning, because from the design, we should be able to estimate how to decommission of our facility. Of course, it is not always the case, especially for very old facilities from the 50s or 60s, when even the documentation we have not in a full volume. But for modern facilities that we are planning today, this decommissioning step should be considered in every beginning in the design of the materials. So if we are looking what is the decommissioning, it is administrative and technical action. So these 2 points are very important for us, that are taken to allow the removal of some or all the regulatory controls from a nuclear or radiological facility. And if we are looking on how technically made, beside the, of course, planning, design of the decommissioning step, cost estimation, if we are looking how it make already in the facility, first step may be, not always, but maybe decontamination of the facility, then dismantling. So we take our facility, we cut it, let's say, by parts to decrease the volume of the equipment, of the radioactive waste. And the final stage, we demolish our facility, our building. If we're talking about nuclear power plant, the decommissioning step, or let's say decommissioning starts with the transition step, and transition step starts with the shutdown of the nuclear power plant unit, or just the shutdown of the facility. And there are 3 main strategies for the nuclear power plant decommissioning. It is either immediate dismantling. So if there is, let's say, no problems with the facility, if everything clear, we can start. If there are not a lot of radioactive materials that cannot be processed immediately, then we are starting immediate dismantling. That means that there is a preparation step, of course, and also only after this preparation step, we have a final liquidation. Or it can be deferred or delayed dismantling. That means that there are some problems either with nuclear fuel or other materials inside the facility that should be stored for some period of time, and only after this we can finally liquidate this facility. Or if it is impossible to remove, for example, not the nuclear fuel, but some parts of the nuclear facility, if it is impossible or economically more efficient, and we can prove that it will be safe, in some exceptional cases, we can use the entombment. So it is disposal in place, that we call in Russia, for example. So that means that we dispose our facility directly in the place where it is located, and that means that we operate after this the repository of this facility. In general, decommissioning is very multi-complex task, not just a complex task, but multi-complex, because it takes into account not only technical details, but also it is financial, managerial, and even social issues. So this is a representation from the IAA online courses, where you can clearly see the difference between the 3 main strategies: immediate dismantling, deferred and dismantling, and entombment. So we already discussed it a bit. And again, when we choose the strategy for the decommissioning, a lot of different issues should be acknowledged. It's again not only radiological factors or some technological issues, but it also takes into account social factors and all the stakeholders in engagement, and also even ethical factors. For example, for people who worked for many years in nuclear power plant, it is really difficult to learn how to decommission the nuclear power plant. It's not difficult from the, let's say, mental issues, because of course they can learn things. They're experienced people with good background, but it is hard from the moral point of view that for many years you worked with this facility and now you have to, let's say, kill this facility, and it is difficult from this moral point of view. So all the, even these ethical and social factors should be taken into account during the decommissioning. If we're talking about the future of the decommissioning, why we are talking now so a lot about decommissioning, because from the 50s there are quite a lot of nuclear facilities, not only nuclear power plant but other facilities that are already old and cannot be operated anymore. So with every year we have more and more facilities that should be decommissioned. So this market or number of the facilities is increasing. That means that it is not only good for environmental purposes, let's say, to make these facilities safe for our and future generations, but also, of course, it is good from the economical point of view for people who are working in this market. So the number of the nuclear facilities for decommissioning is increasing every year again. And it is not only, again, nuclear power plants, but also other, let's say, facilities involved in the nuclear fuel cycle. But not only these facilities, not only the facilities from nuclear fuel cycle, it is also medical facilities, it is industrial sources, closed sources, it is research reactors that are not involved in the nuclear, in the energy production. It is food and agriculture sources, so they are used for sterilization of the either products or the seeds or other, and all these materials, all these facilities should be decommissioned at some point. It is this naturally occurring radioactive matter that are concentrated during the technological process. For example, this is so-called White Mountain, is located not far from Moscow in the city of Voskresensk. It is the byproduct of the production of fertilizers. So they are produced so from the monocyte, no, from the apatites. From the apatites. So apatite is used for the production of phosphorus fertilizers, and apatite contains not a lot of, but some thorium and other natural radionuclides. And during the production of fertilizers, the byproduct called phosphogypsum, so it is mixed calcium phosphate and sulfate. They contains quite a lot of radium and thorium inside, and the leakage of from this, so the water that is released from this mountain, White Mountain, contains the quite high levels of this natural radionuclides. So even this B products from the non-radioactive production. So they produce fertilizers, not nuclear fuel or whatever, but this naturally occurring radioactive matter, they arise not even in such, let's say, simple productions. Also in oil industry or gas industry, they produce this norm radioactive waste. And also, of course, we still have nuclear legacy, not only the liquid radioactive waste storages on the ground, but also area contaminated due to some accidents in many places. I think you know, maybe in your country, I don't know. In Russia, there are some places still exist and with very prolonged territory. It will be another lecture about these accidents during the school. So you can see that there are quite a lot of different types of the facilities, of the sources of radioactive waste, and the facilities that should be decommissioned. So if we are going with this technical implementation of the decommissioning, we are starting with sometimes, not always, with decontamination, and you can see quite a lot of different types, methods for decontamination that can be used. They can be used depending on what types of the surface we should decontaminate, what types of radionuclides, how strong the radionuclides bonds to the surface, etc., etc. So quite a lot of different techniques used for specific purposes. There is advantages and disadvantages, as always, for any technology. So advantages for decontamination, that we reduce difficulties during the decommissioning operation. So that means if we decontaminate materials, they are not so radioactive, and now we can handle them much easier. Or we can reduce the class of the radioactive waste. That means if we reduce the class of radioactive waste, or so we lower the category of radioactive waste, it will be cheaper to store them or dispose of them. Again, so it's a benefit. Even we can reach the levels of radionuclides concentrations so low that the materials can be free to release. So if we sufficient in decontamination, we can release these materials as a conventional waste, and it will be much cheaper than to handle the radioactive waste. But the drawbacks of the decontamination is that during this operation, the workers can get higher radiation doses. Decontamination itself can be costly. So it's always a balance of cost efficiency and the efficiency of decontamination in terms of the financing, and also how much benefits we will get from this decontamination. So it's always balance. Also, it will take some time to implement, of course. So it will, it can make it longer. The decommissioning, and time is money is a very trivial thing, but it's true. And of course, during the decontamination, we produce a secondary waste. And again, depending on the method of decontamination, we can produce quite a lot of radioactive waste, even the liquid radioactive waste, of course. So then there is a dismantling technique. So again, we cut in our facilities part by part. And for this, we can use different method, depend on what we are trying to cut, what we can apply. If it is already non-radioactive or very low radioactive materials, can we use people, let's say, some simple techniques like sewing with hand job, Or if it is very radioactive, we can use, for example, remote dismantling. So again, depending on the facility itself, depending on the equipment, what we are trying to dismantle, depending on the radiation doses from this material, we can use different methods and different plans for these operations. And we can use robotics, and you will have again additional lecture on robotics for decommissioning. And when we remove all the equipment that are radioactive, the final step is demolishing, and here we are using just the conventional methods without any specific equipment. Yeah, if we can use it, either using machines or wrecking balls or just explosions. Yeah. Quite conventional methods. So just a brief conclusion from this introductory lecture that first, nuclear energy, of course, as we are working in nuclear sector, I think everybody agree that nuclear energy is important source of energy. And we should remember, and when we speak with people, should tell them that nuclear fuel cycle, it's not only a nuclear power plant, but it's all the stages from the very beginning, from the uranium mining to the final disposal of either spent nuclear fuel or the high-level waste. And radioactive waste is the result of any activity. If we are working with radioactive materials, sooner or later we produce radioactive waste, either liquid, either solid, or gaseous. And treatment of radioactive waste can bring us a lot of benefits. It can significantly reduce the activity and time of potential hazard of these materials. And the main thing in radioactive waste storage or disposal that we use a multi-barrier system. Even for low-level waste, we use this approach in the multi-barrier system. And one of the points that is good for nuclear energy, that the hazard of from radioactive waste is finite. And as the result of the operation of any nuclear facility is the decommissioning. So it's final and inevitable stage of any use or operation of facility. There is three main strategies: immediate dismantling, deferred dismantling, and entombment. And we see now the growing need in decommissioning, in experts in decommissioning, experts in management in decommissioning. So I think this is main points from my lecture. So this is my last slide for today. Thank you for your attention. Any questions? If you have any questions, I will give you a mic. I see that there is some chats. Sorry. Yeah, I think it's quite late. Name of the organic chemicals, I think, for separation of the radionuclides. So the main chemicals are, as we are talking about, the TBP, it's and other types of phosphor organic chemicals. They are quite conventional. It is either ethers of the phosphoric acid, different kinds, or it can be phosphine oxide, or it is carbonyl phosphine oxides, or it is crown ethers, or it is diglycolides of different structures, some polyethylene glycols of different, again, structure. It is chlorinated decarbolide of cobalt. So some, not crown ethers, but how they called, calixarenes, and other some diamides of carboxylic acids, pyridine, phenanthroline, and many others chemicals. So every process mentioned here uses specific extractants for this system. So, any other questions in chat? I think no. Yeah, sorry for the titles. We will look further that nothing will block the title. Sorry for that. So if there is no questions, Andrei?
Yeah, question.
From now we have a lunch break.
No.
No.
Before lunch.
Before lunch.
Presentations of our participants.
Okay, we can have a short break if you want, or we can start the presentation. Oh, Artemi, question?
Thank you for presentation. So my question is maybe not mainly on the radiochemical topic, but on specifically on spent nuclear fuel. When we're saying that, okay, there is a possibility to reproduce the spent nuclear fuel to the final fraction, so it can be the spent nuclear fuel can be fully reprocessed. But we're talking about the national level of reprocessing, because the plutonium is highly radioactive source which cannot be transferred internationally, and or there should be some specific regulations between the countries, and not all the countries have even possibility to reprocess. It's only like several of them: France, Russia, and maybe UK, but like very few. So when I'm saying about reprocessing spent nuclear fuel, we should understand that on an international level, it's very restricted, because there is a plutonium, and plutonium can be used for nuclear weapon or any weapon. So, I mean, we should just pay attention to it. And my question is, so it's on more on the national level, right? Spent nuclear fuel.
There is plan or project from the Rosatom to make it international project, so that we can take spent nuclear fuel from other countries, reprocess it, take all the long-lived radionuclides, including plutonium, make our own fuel, for example, and bring back only the short-lived fraction, like cesium, strontium, in the form of vitrified radioactive waste, so that the country, the spent nuclear fuel produced, they don't need to build this deep underground repository. They just need to build the repository for 300, maybe 1,000 years. So it's much cheaper than to build the deep underground repository under 500 meters, etc. So the idea is that the spent nuclear fuel from other countries come to Russia, reprocessed, and the country get back only the short-lived radionuclides. So that is quite cheap to dispose or store. And in Russia, we use the extracted plutonium as a source for fuel. And we burn it. So in as a final point, we don't have any plutonium because we burn it. We don't have any long-lived radionuclides because we burn them. So it is, let's say, win-win situation. Then the country get only short-lived fraction of the radionuclides, and Russia obtained not only the money, of course, for this operation, but also the source for the fast neutron reactors. Plutonium is needed for fast neutron reactors.
So no, but if you're taking the spent fuel from, for example, Belarus, you can transfer it between the borders of Russia and Belarus, which is much easier. But if you take it from Egypt and transfer plutonium through the international borders, it can cause a lot of questions.
Yes, but I think it is possible.
Absolutely.
Yeah, of course.
Yeah, I mean, it depends on that.
Yeah.
And the second question is, it's about spent, and when the decommission here and not more experienced, are there also high fractured sources, not like plutonium, of course, but any also so sensitive?
Which
when decommission the facility?
Yeah, of course.
Also,
there are quite a lot of high radioactive materials.
I mean, like this, like not like plutonium, but more or less.
Yeah. It's
also
activated products like cobalt, for example, in the steel or zirconium cladding.
Okay.
So it's many other highly radioactive materials. Yeah.
Okay. Thank you.
Mm-hmm.
Thank you for presentation. My question about radioactive waste.
Mm-hmm.
We are for huge radioactive waste. Can you storage by disposal? But for a small amount of radioactive waste, how can you storage it, and how can transport from place to other place to storage it? Can put it in disposal, or can you put in another area? And the second, what are the kinds of containers and the other to transport and storage?
So normally there are, let's say, central facilities for disposal. Of course, you don't need, if you have a small amount of radioactive waste, you don't need to dispose it directly in the place where they produced. Normally, there are some central facilities where all these small volumes of radioactive waste are transported. So for this, you need certified containers, of course, certified transport, but it's just a normal story to bring all this radioactive waste to one place and dispose them there. Of course, depending on the classification of radioactive waste, on the properties in this facility, they have different disposals for different kinds of radioactive waste. But finally, you will see only hills in this place as a final disposal. If it is low level, for example, radioactive waste, or it will be underground facilities, not deep underground, but just subsurface underground facilities. Yeah. So. Uranium ore. Uranium ore. So the tailings, you mean? Yeah. Some materials, yeah, they are radioactive waste. Mm-hmm. Yes, of course. Yeah. So
also materials.
Yeah, if we are talking about the tailings, of course, there is a complex of actions when we built this, how it's called, I forgot even the Russian word. Чтобы вода не проникала. Yeah. So let's say these materials that yeah, waterproof materials. Thank you. Yeah, waterproof materials below the tailings, and all these radioactive materials should be put it in this specifically constructed basins, let's say, with the waterproof bottom. And then also should be covered with another also waterproof materials, the special channels, let's say, to that water that goes with rains not go down, but will go from the hill to the bottom, Yeah, so the special construction for such kind of radioactive waste, because of course there's different types of classification of radioactive waste. In Russia, we have 6 types of 6 categories of radioactive waste, and such kind of radioactive waste is a 6th class. So that radioactive waste that produced from the natural sources like uranium or as well. And for them, there is specific regulations how to deal with them. They are radioactive waste, certainly, so no question, but the specific constructions for disposal are different from that, but from if we produce, for example, radioactive waste and we in small volumes, yeah, like some ion exchange resins or extra organic extractants, or I don't know, classes from the laboratories, and we conditioned them, we put them in matrix, in cement matrix, or I don't know, in plastic matrix or whatever, and we put them in special containers, yeah. And for these containers, we have a special building or repository facility. Yeah, so it's another story. So because we conditioned all this waste in this specific ways with these specific containers, certified containers that have specific forms, shapes, etc., etc. But for this natural radioactive waste, of course, their volume is very large, and we cannot use, from economic point of view, these techniques. For this natural radioactive waste, this norm waste, there are another constructions for the final disposal with this waterproof bottoms and all this linings, etc.
Okay, thank you.
Okay, thank you. I would like to ask you, keep mentioning special containers. For my project, I was told to find containers for spent nuclear fuel. I did this for a term, a semester. I could not find, so I had to drop it. So I don't know, maybe I missed it in your lectures or something like this.
Yeah, for spent nuclear fuel, yeah, we have different containers because spent nuclear fuel, they have different designs, they have different time of operation in nuclear reactor, so they have different, let's say, levels of radiation. And not only ionizing radiation, but also thermal production. And for specific spent nuclear fuel, you will have specific containers. Of course, there is nowadays the new generation of these containers is a universal containers that you can use for not any type of spent nuclear fuel, but let's say for many kind of spent nuclear fuel. And they're called transport containers, let's say, and they have a specific construction that it's not only shielding to ionizing radiation, as I mentioned, but also it is radiators, let's say, to remove the thermal heat. And but you would like to see some specific details on these containers. Yeah, I don't have it in my presentation, but we will ask if it will be possible to present some. Okay. Yep.
Yeah, sir, I wanted to know that in your presentation, you had mentioned that, every country has its own classification of what is radioactive waste. So shouldn't that be normalized in a way to reduce the waste? So shouldn't No, because you
Because-
said Russia has 6 different
Yes, 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 yes.
classes.
In
And
USA, it's another classification.
Yeah,
In UK, another.
and
Yes.
France, no, it has a different set of rules
Yes.
for classing.
Yeah.
So
that's right.
shouldn't IAEA step in and say, okay, this should be a standard lot? Because
Mhm.
then
Yeah, yeah, I see.
you also mentioned that Russia is trying to get in, like you have a proposal wherein the spent nuclear fuel from different countries will come to Russia, and then you will reprocess it, keep some part of the reprocessed materials with you, and then give the low level waste back. So then don't you think that if no every country has a different classification, Russia will have to spend a lot of
Yeah.
extra inventory on understanding what kind of waste is
Yeah.
coming?
I see. Yeah, there is a point that IAEA cannot force other countries to change the regulations, etc. IAEA can only give recommendations, and every country has a choice to follow these recommendations or not. Of course, many classifications in many countries they are related to the IAEA recommendations, but with some deviations. And it's a good point, yeah, that's as far as we have different understanding of what is the level or category of the radioactive waste. But yeah, I think it's a good point. I don't have an answer now, but yeah, it should be in the table when people will think about it. Yeah. But I think it's always a negotiation between the country. Not, I think it's not like tomorrow all the countries will bring spent nuclear fuel to Russia, and we will think, oh, what is the category of the level? I think it's a very long story, and it always negotiations. Yeah. Any more? Oh, yeah.
During operating nuclear power plant, you said that they used it is ion exchange to remove radionuclide from cooling oil. This radionuclide almost it is cesium 137 and cobalt 59, cobalt 60. They have a high activity. How you treatment this ion exchange after remove this container which contain this large amount of ion exchange and also these materials, radioactive materials.
Yeah, it's a current problem in different nuclear power plants because nowadays all the ion exchange resins, they are stored in nuclear power plants, so they are not reprocessed, or they're just stored. And there are different approaches, and there is no unified approach. Every nuclear power plant can decide by their own what to do with ion exchange. There are thermal treatments or putting them in the polymeric compound. So thermal treatment, also different kind of either pyrolysis or burning, or I don't know, plasma incineration, or so there is no unified approach. It's still, I would say it's still a lot of research work, what is the better way or the best way to handle this ion exchange resins. So there is no only one answer. So you can decide from the, you can open your proposal if you have ion exchange resins and see what people will provide you. Yeah. So, and you can choose what is more cost efficient, more reliable for your building, nuclear power plant building, because you will need some additional buildings or territory to make this reprocessing. So a lot of different factors will play a role. Any more questions? If not, Andrei. So, coffee?
Yes.
And after we will have, yeah. Okay, good. So, does anyone have presentations? Or, oh, Simona. No? Okay. So it will be just stand up. Okay. So now we will have a short coffee break, 15 minutes. Yeah.
Presentations have lunch, so.
Don't eat a lot.
Yes, full enough.
Не знаю. Давай проверим. Странно. Так,
Почему у нас не закончили сейчас кофе-брейк, потом мы еще
Так, сейчас я подумаю, как нам. Ну что, так в таком формате тогда будет.
Человек докладывает, рассказывает о себе пару минут. Не раз нажимаешь, ключик забирается. Тогда уже раз.
So, dear colleagues, let's start our short stand-up with small presentations of yourself. Maybe, so we can start. Simona, you are the only one who has a presentation. Давай. Момент. Just a moment. Да из зала. Да. А что-то не хочет. Писает.
Сломалась система.
Да. Не хочет останавливаться. Sorry, just a moment, maybe two. И сломалось.
I broke the system. I broke the system. There's the time.
Ну, может,
Мне
но
кажется, я
он
пришла и все
спит.
сломалось.
Да, нет. Окей, ну, это повернем.
Красота. Бесконечность.
Видим, я тебя поведу в самую крающую. Вот представляю, какая сейчас радость.
Что происходит?
Они смотрят нашу трансляцию. Она у них 3 часа ночи началась. У них школа онлайн. Они уже не интересны. У них еще работа.
Не знаю. Это чё? Блин. Да, я знаю. Ну что? Sorry, dear colleagues. Сейчас нам скажет. А эта камера так и нет сама, да? Надо будет ее, видимо, перетыкнуть. Давай мы просто запустим. Okay. Sorry for some technical problems. So we will start the presentations of the participants, and we'll start with Simona Shandalova, please.
So hello everyone. I see some familiar faces. So but for those who don't know me, my name is Simona Shandalova. I'm from Slovakia, and I finished actually my bachelor's and master's studies here at the chemistry department at the division of radiochemistry at Lomonosov Moscow State University. My master's was in the project management in the field of decommissioning, which I think Andrei or Vladimir will be telling you about later. I'm also the IEA Maria Skłodowska-Curie Fellowship Program recipient, and now I'm conducting my internship. Now I have graduated, and I'm conducting my internship in Sogin in Italy. It's a state company that deals with nuclear decommissioning of the Italian nuclear fuel cycle. And I am participating in projects of European Commission in the scope of Horizon 2020, which are the PREDIS project, where I'm directly involved in the predisposal of liquid organic waste, and in the Harper's project, where I am involved in the circular economy. So my field of expertise is decommissioning, radioactive waste management, and project management. I think that's all.
Okay, thank you. Cool. And we'll start, I think, just row by row. Just a moment. So...
I'm Ayşenur. I'm from Turkey, and now I'm PhD student, and I'm working on the my thesis right now, and it's about radiopharmaceuticals with using zeolites and radiopharmaceutics together in skin cancers. That's all.
Hello, this is Süleyman Fatih Özmen from Turkey. I'm an associate professor in University of Akdeniz. My main expertise area is low-level radioactivity measurement. Generally, my studies are on radioecological studies. Also, I am working as a counterpart for International Atomic Agency. Okay, that's it.
Hello, excuse me. My name is Angelina Diva. You can call me Diva. I am a final year student in Indonesia. I have planned to join research group in passive cooling system. So I'm so pleasure to join in this program, and I hope we can sharing and have an excellent experience in here. Thank you.
Can we copy it? Just.
Hello everyone, my name is Alda Dwianti. You can call me Alda. I'm from Indonesia. I am a final year student of Bachelor Electronic Instrumentation, and now I am internship in a company in Indonesia. The company engages in service electronics. The company is Schneider Electric. I am as engineer, application engineer there, and I hope this. I hope join this program can hone my skill both of electronics and nuclear. Maybe that's all for me. Thank you.
Hello everyone. My name is Ibnu Itkan. I'm from Indonesia. Same with my friend Angelina Diva and Alda Duyanti. I am truly excited to be a part of the International Summer School on Radiochemistry. Thank you.
Hello, everybody. My name is Artemy Konstantinov. I used to work 10 years in Rosatom. I know I was involved in spent nuclear fuel. And after I moved to the IAEA, International Atomic Energy Agency, I'm working there for 5 years. And now I'm involved in nuclear security. Partly, I do some specific areas of disposal or disused radioactive sources, but more or less with the nuclear security. And along this, I've applied for a radiochemistry master degree. So look like I'm coming back to decommissioning and spent nuclear fuel and what is involved with this. So I'm glad to be here with you. Thank you. You don't mind?
Good afternoon. My name is Miriam Akinyodoyo. I'm a human resource officer. Next. Yes, I'm a human resource officer. I did my undergrad in Cambridge, United Kingdom. I did business management, and like I said, I'm a human resource officer. I work for an organization called NUPEA in Kenya, which is Nuclear Power and Energy Agency. We hope to have our nuclear power plant in 2017, hopefully. Yeah. So NUPEA, formerly known as NEB, which is the Kenya Nuclear Electricity Board, is a state corporation established under the Energy Act of 2019. It is charged with the responsibility of promoting and implementing Kenya's nuclear power program, carrying out research and development for the energy sector. So our mandate is development of infrastructure necessary for the establishment of the NPP in Kenya. The second one is coordinate research and development in the energy sector in Kenya. The third, coordinate capacity building in the energy sector in Kenya. And last, coordination of the IAA technical cooperation projects in Kenya. So we have our NPP is based on a milestone approach. Right now we are in phase 3. So this is a milestone approach. We have phase 1, phase 2, and phase 3. Yeah. So we have the milestone 1 is a feasibility study. Milestone 2 is the bidding process, which we've already done. And then last but not least is commissioning. So the status of our nuclear infrastructure, for example, we have the regulatory framework, which the Nuclear Regulatory Act of 2019 has established a nuclear regulatory framework, which is the KNRA. Yes, the management organization, the nuclear regulatory body KNRA has established NUPER, the organization I work for, as a NEPIO with a clear governance structure. Environmental protection, strategic environmental assessment is in the final stages. We're working on it at the moment. And plan EIA for the preferred and alternative NPP sites. So we've already established our nuclear our sites at the moment. So we're just working on the next phases. Last but not least, stakeholder engagement, which is very important because the public needs to know. You need to engage the public. They need to know what it is that you're doing. So extensive public awareness through academic institutions. So we've worked with, we have people who have come to Russia, who have Rosatom, South Korea, and also the US. Annual MPP visits for political leaders, such as lawmakers. Siting, so like I said, we've already found our site. The SEED mission conducted by the module 1 site survey and selection criteria. Activities for site characterization, ongoing land requisition is underway. Human resource HRD, which is human resource development, training of Kenyan nationals in South Korea, KEPCO, participation in IAA technical cooperation projects on nuclear energy, and human resource development for the workforce. So we have now until 2027 to create that. Industrial involvement, so outreach is ongoing, targeting major industries such as steel, cement production companies. Industrial capability survey and assessment is complete. So this is just what's been going on in regards to stakeholder engagements. For example, members attending the 63rd IAA. We also have the regional stakeholder conference, the 3rd African Conference of Nuclear Energy in Africa, and the Fission magazine that the organization created. So in conclusion, the Kenya's NPP has been on a positive progression due to strong government, national stakeholders, and the energy sector. Allocation of additional funding through operationalization of Energy Consolidated Fund for effective regulation of the nuclear power program, the independence of the nuclear regulator. Nuclear technology has potential to provide economic benefits, reduce emissions of pollutants, and supports the Big Four agenda. Last but not least, the role of international collaboration is the key to successful implementation of the nuclear power program. So yes, thank you.
Thank you.
Thank you. I would like to say a couple of words about the person who is not present at the moment. His name is MD Sankar. He's from Bangladesh. And I'm speaking out of his name because, you know, you've just mentioned the nuclear power program in Kenya. So his absence due to a very, very important reason at the moment, he takes part in building of a nuclear power plant in his native country, Bangladesh. So he will join us later. He will join us on the 23rd of August, and I expect that he will represent himself much better than I do at the moment. But just to, you know, for you to know that there is another person who is not absent, who is not present today. Okay.
Hello, everybody. My name is Aditya, and I come from India. I have a master's in nuclear engineering from the universities in India as well as France, so dual masters. Currently, I work as a visiting faculty teaching students in an university in India about nuclear safety and security and nuclear thermal hydraulics. Since my specialization during my master's was in radioactive waste management, eventually I wish to be a part of IAEA and taking forward decommissioning projects. Thank you.
Okay. Hello, everybody. My name is Sebastián Mamani Cuenca. I am from Bolivia. I'm supporting the nuclear projects in Bolivia, and the lithium projects are started in Bolivia with Russian cooperation too. And I am currently a Russian nuclear education ambassador and student at Tomsk Polytechnic University in nuclear technology. My expectation this event is to learn a lot, to take advantage of the themes, especially the 3D models and robotics. And after this course, I would like to continue supporting the Russian and Bolivian projects. And I will thank you. I would like to thank you for this opportunity. Thank you so much.
Hello, good day. My name is Nurjan. I am from Kazakhstan. I work at National Atomic Company, Kazatomprom, Department of the Nuclear Technologies and Radiochemistry West. Thank you. Good luck.
Hello, my name is Sildar. I'm from Kazakhstan. I job of National Atomic Company, Kazatomprom, Department of Nuclear Technologies and Radioactivity West. My job is decommissioning uranium mines. Thank you.
Hello, everybody. My name is Olga. I'm from Belarus, Minsk. I'm a PhD student at the Belarusian State University Chemistry Department. And now I'm studying the radiation chemical and free radical transformations of biomolecules in aqueous solutions. So that's some processes that happen in human body in cells under the exposure of radiation. I'm very glad to be at this school. It's my second time, and I'm very glad to see all of you, and wish you have a good time here.
Hello everyone, my name is Muhammad Omar. I'm from Egypt. I'm graduated with a specialist degree with the nuclear power plant design and operation in 2022. Now I'm master degree student in Tomsk Polytechnic University, and I'm one of Russian nuclear education ambassador. Thank you.
Hello everyone. I'm happy to join for the second time in this school. My name is Hisham. I am from Egypt. I am lecturer in the Faculty of Science, Lazar University. And at the same time, I am a postdoc researcher in Ural Federal University, Russia. My specialist in radiotherapy, especially in radiation dose to patients from radiopharmaceutical materials. And I am happy to meet all of you. Thank you.
Hello, everyone. My name is Karim Mahmoud. I am from Egypt. I'm working as a lecturer in Egyptian nuclear materials authorities, and also I am a researcher in Ural Federal University. In the last year, I finished my PhD thesis in Oral Federal University in field of radiation shielding. This is all. Thank you.
Okay, Olado, it's a pleasure to be here. Olado Kwanjawale, my own name, from Nigeria. I have a background in civil engineering and an ongoing master's in Tomsk Polytechnic University. I'm studying nuclear power engineering. And I have a vast experience. I have been working with Nigeria Atomic Energy Commission for the past 7 years. And my areas of discipline have been nuclear fuel cycle and radioactive waste management, the nuclear safety, security, and safeguard department. And currently I am now in the nuclear power plant directorate. My own interest and area of interest right now is energy management and construction, as Nigeria is trying to see how to increase its energy consumption right now. So also my motivation for joining this school is after construction, on a long term, you have to decommission one day. So I'm trying to include decommission into my own expertise, and I like to meet like-minded people and contribute my own quota. Thank you.
Good morning, everyone. My name is Yana Ustinovich. I'm from Belarus. I represent Belarusian nuclear power plant. My background is radiochemistry. 5 years ago, I graduated from the chemistry department of Belarusian State University, and since then, I have been working in Department for Radioactive Waste Management of the Belarusian NPP. Among my duties are rad waste characterization, accounting and control, and as well, I'm responsible for supporting the contract between our enterprise and joint stack company as well, concerning decommissioning issues of the Belarusian nuclear power plant. And I'm very glad to be here, and want to thank for the opportunity to take part in this program. And I wish everyone fruitful days. Thank you.
Hello, everyone. My name is Valeria Dmitrieva, but you can call me Valerie. I'm from I'm from Belarus, and by major, I'm radiochemist, and I work in Department for Nuclear and Radiation Safety for the Ministry of Emergency Situation, Republic of Belarus. My duties include supervision over the radioactive waste and spent nuclear fuel management, over the radioactive or radiation objects, for example, some medical objects with radiopharmaceutical and, for example, positron emission tomography, and atomic objects, for example, MPP, radioactive waste storage facility, and I hope radioactive waste disposal facility in the future. I'm glad to be here, and I want to wish us good luck and good cooperation in the future. Thank you.
Hello, everyone. My name is Khalid Ramadan. I am from Egypt. I have finished my bachelor degree and master degree in Tomsk Polytechnic University, and now I am about to make the PhD in the specialist in the hydraulic and heat transfer into the nuclear power plants. So I wish us a good time, and I'm glad to be here. Thank you very much.
Hi everyone, Assalamu alaikum wa rahmatullahi wa barakatuh. I'm Basim from Iraq, Basim al-Mayahi. My bachelor in physics, Department of Physics, University of Babylon University. And I have a master in physics also, but nuclear physics in my field or specialization in nuclear physics. This one radiation shielding. And I have a PhD from USM in Malaysia, 2010 until 2023 in field of environmental radioactivity. Also, I have postdoctorate fellow research in University Malaya, 2023 until 2024. In radiotherapy, this one in nanoparticles. Also, I can enhance the cancer treatment or enhancement with radiotherapy. I'm professor now in University of Kufa in Iraq. Supervisor for one PhD student and master about 6 students. I have 150 articles published already in local and international journals in Scopus and Clarivate. Also, I have 4 books already published. We can find it in online. Participate in many conferences in local and international. This one just briefly to my, I just now I writing about myself. So I'm glad to enjoy and participate in this event, ISSR 2023. I have to participate. So this one 3rd times I'm here. So I'm glad to participate and enjoy. Also, I would like to thanks all organizer to give me this invitation to participate here. Thank you so much.
Hello, everybody. My name is Nadezhda Zdanevich. I'm from Belarus. 20 years ago, I graduated International Radio Ecological University with specialization on nuclear physics and radiochemistry. About 10 years, I worked as engineer designer and developed a lot of technical and design documentation on environmental and radiation protection. After that, I worked in Ministry of Natural Resources and Environmental Protection of Belarus and was responsible for such question as state ecological expertise and environmental impact assessment in transboundary context. And during this work, I was official representative of Belarus in implementation committee of ESPA Convention in Geneva. Do you know UNICE? Yes. And from 2020, I'm head of technical support department in Belenerga. Belenerga is a managing organization for nuclear power plant in our country, and our department is responsible for organizational and technical methodological issues on radiation protection, nuclear safety, physical protection, radioactive waste management, and so on. Thank you for opportunity to take part in this very, very useful event. And I want to wish everybody fruitful work here and new cooperation. Thank you.
Hi to everybody. My name is Mikhail Kovalenko. I'm too from Belarus, from Belenerga. I have background about 15 years. I was worked on field of radiation monitoring, and last 2 years I work in Belenerga in position leading engineer for radioactive waste management. In my professional duties in technical support of processes of radioactive waste management on Belarusian NPP. In that way, I think that that experience that I received for next 2 weeks was very useful for me, and it's very good knowledge that I think I received very good knowledge this week. Thank you.
Good afternoon, Moscow. Good afternoon, organizers. Good afternoon, participants. I'm Evgeny Usik, leading specialist, subdivision of strategic planning and development, division of radioactive waste management, Department of Nuclear and Radiation Safety, Ministry of Emergency Situations, Republic of Belarus. Yes, it's really a long name. Typically, it takes 4 lines in Word. So if it's to say easier, regulatory body. Thanks to organizers for such opportunity to learn something new, knowledge, people, experience. I wish it will be very useful for me. Thanks and best regards.
Hello, everyone. My name is Muhammad Hanafi. I am Egypt. I have studied bachelor degree and master degree at Egypt, and studied PhD at Ural Federal University, Yekaterinburg, Russia. But I defended it at Tomsk Technical University. And this year, I get a postdoctoral researcher position at Ural Federal University. My interesting topic, environmental radioactivity and radiation protection. I am so glad to thank the organizers and the groups in the last school, and I hope to get useful information from this event. Thank you very much.
And we have participants online. So please, Laura.
Yes, hi, can you hear me?
Yeah.
Okay. Good morning, I am Laura Nisnik from Argentina. I belong to the Radioactive Waste Management Program from the National Atomic Energy Commission of Argentina. I have a PhD in physics, particularly in nuclear fuel, accomplished in the materials department of the commission. And since last year, I am serving at the Radioactive Waste Management Program, starting projects in the area of decommissioning of nuclear facilities and spent nuclear fuel. And I'm also the contact point between the program and the nuclear power plants operator. I wanted to thank you very much for the opportunity for us to join the school virtually from Argentina. We are a group participating from the Radioactive Waste Management Program. Some of us joining today, others probably tomorrow, because it happens to be a non-working day this Monday in Argentina, but probably the next days, some of us are joining also. So thank you very much.
Thank you. Anyone from online? More? So, okay, if not the case, then thanks again for all the participants for the presentation. Now we will have a lunch break till Andrei, till 2? Dadu? Till 3 p.m. in Moscow.
We will return in a minute, Andrei, and we will advise you how does it work with your lunch, okay?
Okay, we'll come back in 1.5 hours. Sorry, one more. Dr. Huda Farid would like to present herself. Please, 1 minute attention. Yeah. Dr. Farid.
Hello, everyone. My name is Hoda Farid. I am from City of Scientific Research and Technological Application, Alexandria, Egypt. And I am my specialized is nanomagnetic particles and its application in radiation shielding and so on. I'm very interested to be here with you, and it's my pleasure to be with you. Thank you.
Thank you very much. Thank you.
Thank you.
Okay, now, yeah.
Okay, so please. So every day we will give in tolerance. So you can
Начинаем, да? Good afternoon, dear colleagues. My name is Yulia Gorlova, and I represent 12 fuel company integrator for decommissioning and red waste management. It is Rosatom's integrator for all activities in decommissioning and red waste management and rehabilitation of territories and other related subjects. Today, I'm happy to accompany you on the virtual journey through competences of Rosatom in this area. And we will talk about decommissioning and red waste management and remediation of territories. And during our today's virtual tour, we will get acquainted with the main processes and stages of decommissioning. And we will touch upon related works that happen during these processes and what radioactive waste management and rehabilitation of territories features along this way. And we will also tell you about Rosatom's experience, references, products, services, and technologies that we represent. So let's start.
Rosatom is a leader in the global market of nuclear services and technologies. The corporation demonstrates, for example, how to reliably control and safely use limitless nuclear energy. The corporation's foreign portfolio includes 34 state-of-the-art power generation units in 11 countries. Rosatom provides its partners with a unique offering, turnkey nuclear power plant construction and service at all stages of nuclear power plant lifecycle. Managing the lifecycle of a nuclear facility, from the decision to build it to decommissioning, is an important strategic task that entails ensuring sustainable development of the nuclear power industry. Solving tasks regarding safe and efficient decommissioning and shutting down nuclear and radiation hazardous facilities, as well as issues of radioactive waste management and site remediation, are priorities and promising areas of activity. In 2019, fuel company TEL was appointed by State Corporation Rosatom to be the industry integrator in the following business area: nuclear decommissioning and associated radioactive waste management. The fuel company of Rosatom TEL is one of the world's largest suppliers of nuclear fuel. TEL is a monopoly supplier of nuclear fuel to all Russian nuclear power plants, ship and research reactors. TEL fuels MPPs in 14 countries, that equates to every 6th power reactor. TEL incorporates enterprises that specialize in making gas centrifuge machines, uranium enrichment, and fabrication of nuclear fuel, as well as research and development organizations. The Rosatom Decommissioning Integrator is a one-stop shop for cooperation between Rosatom and its partners and customers on nuclear decommissioning and radioactive waste management. Accumulates, centralizes, and consolidates the competencies of nuclear industry organizations in the area of nuclear decommissioning. Develops a comprehensive product offering a full cycle of services from pre-design studies, design documentation development, to dismantling of equipment and structures and site remediation after decommissioning is completed. Coordinates nuclear decommissioning activities, optimizes the allocation of industry resources, develops human resources potential, and creates educational platforms to improve employee competence and retraining. Builds supply chains in Russian and foreign markets, finances research and development projects, contributes to the achievement of the Sustainable Development Goals developed by the United Nations.
So we go ahead. As per today, there are 58, not even 56 as shown here, but we developed, so there are 58 companies that are included in the infrastructure and business area, nuclear and radiation hazardous facilities, decommissioning and waste management for associated waste. And Rosatom has got a portfolio that includes more than 100 successfully realized projects, finalized projects in more than 20 countries, and there are more than 50 products that we offer for the market, including technological solutions. And we will show you the most significant competences and products that we have. To begin with, let's look what is a nuclear and radiation hazardous facility and why is decommissioning of it is so important.
Nuclear power is an essential component of the global energy complex, accounting for about 70% of electricity production. It can be a guarantee of the economic and energy independence of states, provided the safety of its use ensured naturally. This is the relevance of decommissioning. We should be able not only to build, but also to competently complete the life cycle of a facility. There are now about 138 nuclear power units in the world, not including experimental, industrial, research and transport reactors, as well as sites which have been shut down, are in various stages of decommissioning. One of the leading scientific centers in the world's nuclear power industry, the Radium Institute in St. Petersburg, celebrated its 100th anniversary this year. It wasn't the only organization in the Soviet Union that used radiation hazardous materials in its processes. Today, there are over 100 such enterprises in Russia alone. Uranium mining and enrichment, production of nuclear fuel and ionizing radiation sources, generation of electricity and heat at nuclear power plants, storage of spent fuel, disposal of various radioactive wastes. All types of facilities eventually end their operation and must be safely decommissioned and the area remediated. Just imagine a natural park would appear in the place where the nuclear power plant is today, a garden city or another Disneyland. You're probably asking how is that possible? The answer is here at Twell Fuel Company, where Rosatom is creating a new resource and scientific base.
Decommissioning is an integral part of life cycle of any nuclear facility, and decommissioning can be performed in one of two ways, as in situ disposal or liquidation of the nuclear facility. Rosatom has its own experience in situ liquidation, in situ disposal of the nuclear facility. This approach was used, for example, for decommissioning of industrial uranium graphite reactor at the facility of Siberian Chemical Combine. And now it's the place for pilot demonstration center for decommissioning of uranium graphite reactors.
In situ disposal of a nuclear facility, this approach is adopted for decommissioning of industrial uranium graphite reactors, and Rosatom already has such experience. Remember the Disneyland thing? We're already one step ahead. It's a small hill now, but once upon a time, the Siberian Chemical Combine's first two-purpose industrial reactor was located here. The pilot and demonstration center for decommissioning of uranium graphite nuclear reactors was the first to gain experience in completely decommissioning this type of reactor in 2015. During implementation of this unprecedented project, Rosatom specialists did a huge amount of research, the results of which justify the safety of the adopted concept and design solutions. The decommissioning service worked out and implemented the technology for the creation of external and internal safety barriers during disposal of the reactor unit and performed a full range of practical works. The E12 industrial uranium graphite reactor, commissioned in 1958, was shut down in 1990 and disposed of in situ in 2015. On the site of the nuclear reactor building E1 and 2, there is now a special radioactive waste conservation facility in which radioactively contaminated elements of structure are reliably isolated from the environment. Before, when there was a reactor building at this place where we're standing, the permissible operating time was 7 hours. Now, after the completion of all the work, the background radiation has dropped 8 times. Here, the natural background radiation is the same as at the whole site. All non-reactor equipment in the reactor building was dismantled, containerized and placed at the storage site. The low elevations were backfilled with barrier materials based on natural clays. A specially selected and treated composition using a special technology was filled into the reactor. It's not just filled in, it's compacted and an engineering barrier is created. It prevents radionuclides from escaping from the metal structures of the reactor shaft. From the graphite stack, and if it happens that radionuclides escape, it absorbs and doesn't release radionuclides into the environment. Considering experience of technology on barrier materials at the site at Seves, we started decommissioning another industrial uranium graphite reactor with a mining and chemical combine in 2013. When the mining and chemical combine received a gold medal in the energy category at the Inventions Geneva exhibition for its patents, method of decommissioning a uranium graphite down-type nuclear reactor. The uniqueness and at the same time the complexity of this work lies in the facility's location. It lies in an underground mine in a rock massive at a depth of over 200 meters. There is a clear connection with the name of the Rosatom State Corporation's division, Environmental Solutions, which includes the mining and chemical combine. Today, the mining and chemical combine's activity is centered on the environmental safety of nuclear technology. The main source of radiation hazard is the reactor graphite stack, that is, the reactor core. There, a nuclear reaction was going on for decades. The main task of decommissioning is to create a protective barrier around it, which will reliably prevent radionuclides migration to the entire period of hazard. In fact, it's necessary to build an absolutely hermetic and immovable architectural structure around it, which retains its protective properties and also takes into account possible geological changes. All the nuclear fuel that was in the reactor at the time of shutdown was unloaded and reprocessed at our radiochemical facility. Radiation contaminated equipment involved in the main technological process was dismantled from the new reactor sections as much as possible. The sections could be subsequently filled with barrier material. To prevent natural degradation of the existing metal structures, the sub-reactor section was filled with high-strength reinforced concrete. One of the main tasks was to localize as much as possible those radionuclides that had accumulated in the graphite stack throughout the reactor's lifetime. To do this, we solved the not exactly trivial problem of supplying barrier material. The band-free filling of the graphite stack and sections involves creating a monolithic structure that prevents the radionuclides in the graphite stack from spreading into the environment. The option of radiation-safe in-situ disposal of reactors eliminates a significant amount of radiation hazardous work and avoids the creation of additional facilities for the disposal of highly radioactive waste from the graphite stack bricks. In addition, the presence of a natural outer containment in the form of a rock massive over 200 meters of granite above the facility is also an advantage of this decommissioning option. Taken together, all this will ensure compliance with modern requirements for radiation safety and prevent releasing radioactive substances into the environment.
Well, here you have just seen how the option of in-situ disposal can be implemented in our practice. But at present, the preferred option of decommissioning, and also the one that is recommended by International Atomic Energy Agency, is the option of liquidation. And this approach can be implemented in 2 ways, as deferred nuclear facility liquidation or immediate liquidation of nuclear facility. In case of deferred option, the works on dismantling and decontamination and further disposal begin after the safe storage of all the systems, structures and components on site, sometimes for several decades. That's because we have to wait until the contents of radioactive substances will get to some acceptable levels to permit works for the personnel. In another option, that is immediate liquidation of the nuclear facility, works on dismantling and decontamination can be begun immediately after the facility is shut down and works are terminated. And further, we will explain how the decommissioning process is structured on the example of immediate dismantling. And along this way, we'll show how experience of Rosatom is used and which promising technologies and already reference technologies can be used along this way. Let's go ahead. Okay, so shall we go into that? Yes, so in the just some words before that, in the zero stage of this process, of decommissioning process, we get to the stage of preparation for decommissioning. And this stage includes performing a comprehensive engineering and radioactive survey, design and obtaining license upon getting all the necessary documentation, and creation of necessary infrastructure, because definitely not all the needed equipments, workshops are available at the site after the operations are ceased. And definitely this stage, although it's only a preparation stage, it's really important and we shouldn't under-evaluate it. For example, one of the substantial elements of it, this comprehensive engineering and radiation survey, if performed well, it allows us to identify correctly the flows of waste and to plan equipment that will be needed for decommissioning, and also to plan what are going to be the costs for a decommissioning program. And let's examine the stage in more detail. Preparation and decommissioning. Yeah.
The preparatory stage includes important sub-stages: final shutdown of the facility, unloading spent nuclear fuel and nuclear materials, and removing them from the site, bringing the facility into a nuclear safe condition, removal of working media, routine decontamination of equipment and premises, carrying out a comprehensive engineering and radiation survey, developing a concept of the facility's decommissioning with a feasibility study of decommissioning options and selecting the most appropriate one, developing the facility's decommissioning program, developing the terms of reference for the project and the decommissioning project, preparing a safety analysis report, developing a set of documents to obtain a license for decommissioning, obtaining the license, creating the decommissioning infrastructure, necessary facilities, communication lines, upgrading service systems, etc. Work at this stage results in obtaining a license for decommissioning. The necessary preparation stage for decommissioning is a comprehensive engineering and radiation survey, CERS. This entails organizational and technical measures necessary to obtain initial data for decommissioning the facility. It consists of an engineering and radiation survey. Within the framework of the first one, the characteristics of the premises, a list of systems, a study of equipment and communications, and information on the actual state of the facility is collected. The radiation survey includes a list of facilities exposed to radioactive contamination, quantity and characteristics of accumulated radioactive material, volume of accumulated radioactive waste in storage facilities, their specific and total activity, radionuclide and chemical composition, gamma radiation dose rate from equipment and radioactive waste storage facilities. On the basis of the CERS, a concept for decommissioning is developed, followed by the decommissioning program of projects. In the future, Rosatom expects a significant increase in the number of facilities to be decommissioned. For a long time, preparations for the decommissioning process are one of its main elements. The comprehensive engineering and radiation survey were conducted the old-fashioned way on paper. At present, the technology of creating a digital operating radiation engineering model, DOREM, of the facility is used. The Digital Comprehensive Engineering and Radiation Survey is a process of obtaining data on the engineering and radiation condition of the site. When the collected actual and archived data have a digital format and a systemized structure, this means that the collected data is purposefully grouped around a previously prepared framework, a DOREM, of the site's radiation hazard. As a result, the information engineering radiation model obtained after the DOREM, which displays the actual configuration and state of the facility, becomes the basis for the digital decommissioning design. Applying DOREM provides a fundamentally new level of preparation of initial data that corresponds to the actual state of the facility, which significantly improves the quality of the results while reducing labor intensity. There are no analogues in Russia's nuclear industry and in the world of applying an integrated approach of decommissioning using digital technologies, laser scanning, spherical panoramic photography, creation of photo tours of all the site, buildings and structure, integrating the radiation components. This technology can be widely applied not only in implementing decommissioning projects, but also with preparing the decommissioning concept during the formation of the decommissioning program and at all stages of the facility's final life cycle. The Siberian Chemical Combine's radiochemical plant is a unique facility. In the past, it processed irradiated standard uranium blocks from industrial uranium graphite reactors. Now it's an operating facility for refining uranium feedstock from the 12 Fuel Company. This is the largest nuclear and radiation hazardous facility, exceeding 5.5 times the volume of the RMPK 1000 units. Stage 1. A DOREM of the building and structures of the radiochemical plant was created. Work digitizing all available documentation, 11,000 documents was carried out. Laser scanning and spherical photography was made, including 3,500 photopanoramas, 2,000 scanning points. Using 3D modeling tools, a digital twin of the plant was recreated. The created digital model of the radiochemical plant, in its complexity, content, and scale, is the nuclear industry's first experience in implementing the decommissioning project using digital technology.
Decommissioning activities can begin when the license of the regulator is obtained, and the major aim of the decommissioning process is to bring the facility to the end state that is chosen by the operator and approved by the regulatory body. The main stages of decommissioning include dismantling of equipment and structures, decontamination of equipment and structures and components, radioactive waste management that actually happens all through the way of the decommissioning process, and remediation of territories that normally goes as the last stage of the process. We will proceed to dismantling part. Here we go. Dismantling. Mm-hmm.
All equipment dismantled in metal structures, except contaminated ones at the decommissioned facility, are reusable material, and after decontamination, they return to general industrial circulation, up to 90% of equipment. Contaminated structures, vessel internals, reactor pressure vessels, etc., and fragments that didn't pass the final radiation control are considered solid radioactive waste of different activity levels, including high-level solid radioactive waste. Various products, including frame structures and long parts, are dismantled and fragmented. A special task involves dismantling, fragmentation, and fragment handling of vessel equipment with wall thickness of up to 300 millimeters. Steam generators, reactor vessel, and vessel internals. We perform the following key works: fragmentation of vessel internals, dismantling and fragmentation of the reactor vessel, dismantling production and engineering equipment, dismantling building structure elements, dismantling buildings and structures of the infrastructure and basic facilities if necessary, conversion of facilities. Rosatom has big experience in using conventional fragmentation and dismantling methods. We also have unique solutions that allow dismantling to be done faster and more efficiently compared to standard methods. Plasma cutting, contact cutting, abrasive water jet cutting, oxygen cutting, mechanical cutting, laser cutting.
After the stage of dismantling and segmentation of equipment and building structures, we move to the stage of decontamination. And to be honest, it can happen before, during, and after dismantling. Rosatom possesses a wide range of different solutions and techniques for decontamination, as such for metallic waste, structures and components, other solid materials, and bulk materials such as soil, for example. Just as it was advised, maybe it would be interesting to have a short look also at some of the most interesting approaches for cutting, for fragmentation, and we propose to have a short look of laser cutting technologies.
Based on commercial interbeam biolasers, the joint stock company State Research Center of the Russian Federation, the Choice Institute for Innovation and Fusion Research, created a family of mobile unit systems designed to perform a wide range of operations, including remote laser cutting and fragmentation of equipment as part of nuclear decommissioning. The separation cutting method, the spatial metal structures up to 440 millimeters thick, allows for fragmenting metal structures at a distance of up to 100 meters and transferring laser radiation through a flexible transport fiber. All the laser systems, equipment, and service staff are located remotely in a clean area, which reduces the dose effect on people and increases time available for continuous work. The system's energy efficiency is up to 35%.
Let's also have a look at dismantling of graphite stack, which is also quite peculiar set of works that is quite demanded and should have good prospects for the market for operators of graphite reactors.
An industrial EI or ADE uranium graphite reactor can be safely disposed in situ, but decommissioning RBMK type power reactors, high power channel type reactors, involves complete dismantling, which needs technology to dismantle the graphite stack. The graphite stack is located in conditions of high radiation fields and contains the main amount of long-lived radionuclides. Human presence in this area is ruled out. A team of specialists from the scientific and design companies, the Decommissioning Pilot and Demonstration Center for Decommissioning of Uranium Graphite Nuclear Reactors, proposed such a technology. To do it, a mobile robotic complex was developed and manufactured and tested at Sever's Industrial ADE-5 reactor. When developing the technology, several options were analyzed. The one providing minimal radiation exposure to personnel was chosen. First of all, the technology allows us to avoid dismantling the reactor's biological shielding system. An opening is arranged in the reactor structure, into which our robotic complex is immersed. And in the high field area, where the graphite masonry is located, the robot then performs all the operations required by the technology, while the operator is in a safe zone. The robotic complex has extensive functionality. This includes moving inside the zone, cutting metal and extracting and moving graphite blocks. The robot's also capable of replacing tools on its own without operator involvement.
So you have also seen some solutions for treatment of irradiated graphite. This is a reactor type application, and such technologies or other technologies are also tested for research reactors, for example, as in Moscow, in Kurchatov Institute, where Mir reactor was decommissioned, Mir and RFT. And now we can move to the stage of decommissioning, which I already highlighted. So as we mentioned, there are various techniques for decontamination based on the type of the material that needs to be decontaminated. And so let's have a look at the solutions that we have.
Decontamination means removing radioactive substances from the surfaces of equipment, machinery, and building structures. The main decontamination methods include mechanical, electrochemical, thermal, laser remelting methods, and their combinations. The following works are performed during decontamination: surface decontamination prior to dismantling, decontamination of equipment dismantled and building structure fragments, decontamination of structures of buildings and facilities after dismantling, Rotterdam's companies apply more than 10 decontamination methods. Abrasive glass decontamination, cryogenic blasting, metal, shock blasting, metal, pyrometallurgical decontamination for metal, electrochemical decontamination, ultrasonic decontamination, laser decontamination, liquid decontamination for metal, decontamination with concentrated ozone.
If you would like, we can also have a look at some exact solutions for this process for decontamination. For example, maybe ultrasonic.
To combine unit for electrochemical and ultrasonic decontamination. Ultrasonic decontamination achieves much higher decontamination levels compared to traditional methods, such as liquid decontamination. Combining the ultrasonic and electrochemical treatment methods enables further increasing the decontamination level and increasing process speed. The result is the most complete removal of surface contamination.
So as you can see, some techniques, some solutions can be combined together to increase the efficiency of decontamination. Some other types like laser decontamination can be also interesting to have a look at with a video.
Laser decontamination. The experience of using laser decontamination at the Siberian chemical plant showed its effectiveness in decontaminating objects with complex geometric shapes. The unit is effective for decontaminating alloy steels, non-ferrous metals with an oxide film. It can be used in combination with other decontamination methods, such as liquid decontamination. As part of research and development work, we got good results on decontamination of non-ferrous and stainless metals. The relevance of the method is due to the fact that during decontamination of complex geometric surfaces, it is very difficult to get close, for example, with a grinder, or let's say that after the chemical method of deactivation, not all areas have been deactivated to the required standards. And it is the laser that has the ability to penetrate into hidden surfaces, those of irregular geometry, and by heating, vaporize the radioactive contaminations from those very surfaces, which aren't amenable to other mechanical methods of decontamination.
And I propose to have a look also at pyrometallurgical decontamination, which is also quite peculiar.
The listed decontamination methods are only suitable for cleaning radioactive deposits that remain on the surface. But what about deeper contaminants? Pyrometallurgical decontamination is used to decontaminate metal wastes that are characterized by a great variability in morphology and radionuclide composition of contaminants. The metal is fragmented to a convenient size and loaded into an induction smelter. In the induction crucible, the metal is melted to a temperature of 1,550 degrees. Various flux additives are added to the melt. The radioactive particle is assimilated in a side layer, which is subsequently removed, and the metal, cleaned to sanitary standards, is poured into molds for subsequent transfer for reuse.
So as you can see, there are various solutions, and they are chosen or combined or made in sequence so that to make the process of decontamination optimal and to achieve needed decrease of level of contamination. After this stage of decontamination and dismantling, we move to the discussion of matters of radioactive waste management. Let's look at the different type of classes of waste and at the stages of waste management. We will also show you some examples of solutions that we have for that, and definitely just worthwhile to mention that this process is really important, almost crucial, because the more efficient is our waste management, the less waste finally goes for the disposal.
Radioactive waste means materials and substances that are not subject to further use, as well as equipment and products, including spent sources of ionizing radiation in which the content of radionuclides exceeds the levels prescribed by sanitary regulations. In terms of its aggregate state, radioactive waste can be solid or liquid. In terms of radioactivity, radioactive waste is categorized as highly active, medium active, low active, and very low active waste. Radioactive waste management stages. Removal of accumulated solid radioactive waste from storage facilities. Collecting and sorting radioactive waste by aggregate state. Morphology and processing methods. Processing, modifying physical form, aggregate state, etc. Burning, pressing, decontamination, and conditioning of solid and liquid radioactive waste, rendering it suitable for disposal. Transportation of radioactive waste, aerial of radioactive waste, optimizing radioactive waste management procedures.
Let's have a look at some examples, for example, for solid waste. So generally, there are waste streams for the different types of waste. And first, we make the sorting. So as for the waste stream for the solid radioactive waste, it can go different sets of procedure and solutions to treat it, and further go to the stage of storage and finally disposal. Let's have a look.
The anthropomorphic robotic manipulator copies the operator's movements and reproduces them at the worksite using a robotic system. The distance with work performed is up to 100 meters, and the weight of objects being handled is 50 to 100 kilograms. The anthropomorphic robotic manipulator is a trunk-type robot, having two multi-link manipulators with electric propulsion drives and working bodies in the form of mechanical hand-like grippers. The robot is remotely controlled by the operator using a copying control device provided with stereoscopic machine vision. Purpose: to work in enclosed spaces with possible space restrictions. The manipulator is composed of a head module, manipulator module, 2 pieces, gripping modules, 2 pieces, a trunk module. The manipulator module is intended to carry loads and includes 2 electric propulsion drives. The gripping module is a mechanical anthropomorphic gripping device. The gripping module is intended to handle objects, operations of gripping, rotating, moving objects of arbitrary shape with limiting parameters, no more than 30 centimeters in each dimension, and a maximum weight of 15 kilograms. When gripping, using 2 manipulators with a gripping module, the maximum weight is 25 kilograms. In cases of elongated objects, the linear dimension shouldn't exceed 60 centimeters.
Let's also have a look at the solution for compactation of the solid waste. That is a super compactation unit. So basically, okay, I will explain later.
In 2014, Seattle Chemical Engineering Research Institute supplied a high-pressure press, the so-called super press, in the Voronezh MPP-2. This is the first domestic equipment of this class implemented at the Russian nuclear power plant. The high-pressure press is part of the equipment for solid radioactive waste management. It can achieve 10 to 12 times reduction of solid radioactive waste volume through 2-step pressing with the use of low-pressure press at the first stage, which reduces the volume of radioactive waste by about 5 times. This pressing is done in standard 200-liter drums, which are then put under a high-pressure press. The briquettes resulting from this processing are loaded by a special manipulator with a stacker into a non-return protected plant, which is then delivered for storage or disposal. This technology makes it possible to significantly increase the waste volume reduction ratio and to use the storage areas for conditioned forms of radioactive waste in a more cost-effective way.
I just wanted to mention that if we're talking about compaction, there can be the preliminary compaction machines that have less pressure, and the big ones that can be used and chosen depending on the needs of the facility, where you really have to make big impacts to the metallic structures to press. Let's also have a look at other solutions, like the ones for liquid radioactive waste.
It's very dangerous to keep liquid radioactive waste without turning it into a solid phase. There's always the possibility of depressurization of the container, and the risk increases many times with prolonged storage. Therefore, conversion into a solid phase is required for safe storage of radioactive waste. The unit for cementation of liquid radioactive waste is developed for cementation of liquid radioactive waste of low and medium specific activity. The operation principle of the unit is quite simple. Cement with additives is fed into the mixer, while the waste from the liquid radioactive waste measuring containers is fed simultaneously with cement. A container is pre-installed under the mixer. The cement mixture with liquid radioactive waste is fed into the container, which is sealed after filling and transported to the repository. The unit is fully remotely controlled. Transport operations with the container are carried out using grippers. The thickness of the container wall enables completely excluding the impact of ionizing radiation on personnel health. The cement compound has a sufficiently solid structure, and therefore the release of radioactivity is excluded. That elemental base that's poured into the cement compound is either bronze or non-return protective cast. It ends up being an additional barrier that prevents radioactive waste from escaping into the environment. It's important to note the process of cementation of liquid radioactive waste is considered to be the most universal and simple method for the binding and fixation of solid and liquid low-level radioactive waste. These cementation units are used in all types of MPPs. The containers are non-returnable and guarantee long-term and environmentally safe storage of radioactive waste.
So not only dangerous, but it's not even allowed by the legislation in Russia to store non-conditioned waste as liquid waste. That's why it's really important to condition that using such technologies as you have seen here, the cementation or ion exchange sorption and some others that are available. We can also see if there is available. Yes, here for membrane complex routine.
The Ruche modular membrane junction complex was developed to process low and intermediate level liquid radioactive waste. Ruche is a mobile unit based on a standard 40-foot shipping container. The unit's mobility enables solving the task of decontamination of liquid radioactive waste at the places of its generation. Radioactively contaminated water is decontaminated by a selective absorption method. The operating principle is one of ion selective purification of a modular membrane absorption complex. Ruche is based on properties of selective absorption of radionuclides by special agents with subsequent filtration through the system of ion exchange filters. Decontamination of radioactively contaminated water from cesium and strontium radionuclides is performed by water treatment with thermoxide sorbents. Unit capacity for treated water, nominal 500 litres an hour, maximum 700 litres an hour.
So let's also shortly take a look at certification. That is a part of the process that is kind of essential for conducting any kind of works.
Certification of radioactive waste packages entails measuring the gamma radiation energy spectrum, determining the isotopic composition and specific activity of gamma-emitting radionuclides of solid radioactive waste in packages of various shapes and geometries, measuring the gamma radiation dose rate from packages and surface radioactive contamination of packages' outer walls, in order to document the acceptance criteria for the disposal of radioactive waste packages. The Agas Electrolysis Chemical Plant Radiation Safety Service is an accredited testing laboratory. The laboratory equipment can certify radioactive waste packages at all stages of decommissioning and radioactive waste packages obtained as a result of operational activities.
After the waste is certified, checked and certified, it can go to storage or final disposal. And final stages of decommissioning of the site are related to remediation of the site. So when demolishing of the buildings and structures is performed, after that we have to check whether the site itself, the soils, are not contaminated with some spillage or other accidental getting all the contaminants into the grounds. And this process can take actually quite a long time, depending on the techniques and solutions that an operator has for checking this lands for contamination. That's why it's really useful to have solutions that allow you to perform these works in some flow approach and make it, it can allow the process to get in a shorter time frame and also to have a good economy on the costs. So let's have a look at the solution for this.
In practice, the rehabilitation of the environment in areas where nuclear facilities are located means not only clearing industrial sites of the former production facilities, creation of ground covers for depleted ore dumps or tailing dumps, dismantling of contaminated buildings, decontamination of equipment, or dispensing type sites, rehabilitation, and in some cases recultivation, provided the territories are used in the national economy, as well as remediation, reduction of risks and radiation doses, is a long-term process of essentially justified return of contaminated territories to a useful and socially acceptable aesthetic condition.
Go to premise. Yes, let's also have a look at the solution that we have for characterization and sorting of the soils and other bulk materials. That's called premise. And we have references of its operation in Russia, in Angarsk, at our ISSR plant.
The premise unit developed by moving technologies, a member of the plant company, is designed to separate radiation from hand-making bulk materials by flow gamma spectrometric measurements on conveyor, followed by automatic sorting according to specified limit values based on radiation vector. The technology is able to separate the material into three classes according to the purpose-specific activity, depending on the measurements results, to separate clean material from contaminated, and to separate contaminated material into two streams for further treatment according to the level of contamination. The key advantages of the premise unit are high throughput, process automation, which virtually eliminates the human factor and mobility. In addition, the system allows for characterizing various types of bulk materials, soils, sand, slag, and even crushed concrete and bricks.
The solution that you have just seen here in the video, it's not only allows you to characterize, so to define the spectrum and contents of contaminants in the bulk materials, but also it helps to sort that into batches, into different waste streams, and to have in the end some big bags, for example, with waste, some conditional waste, and the free release material. So that's a substantial economy also of money and resources for sending the waste for the storage and final disposal. And out of our experience, this can also bring to substantial economy regarding the time and money that an operator has to spend for keeping the license for the facility. Since the works are not yet finalized, it's like physical protection and other things. So when you use a technique that allows you to have this time economy that equals to months, sometimes even years, that's really a huge pile of money and the ability to make the site more safe, let's say, in the period of just some dozens of months. Of weeks, sorry. So we come to the final stage of decommissioning. We finalized already the remediation of the site, and let's think what happens to the waste. Yeah, because we have to send waste somewhere. It is sent for storage or for final disposal. And that's also a very important aspect of the process, and also something to deal with operator and regulator and to be considered for the whole life cycle of the facility. Let's have a look.
All options for a near-surface disposal site for radioactive waste are based on a system of passive safety barriers to prevent the migration of radionuclides into the biosphere or a significant slowdown of its process. For this purpose, we use various combinations of artificial and natural barriers. The parameters of barriers used can differ significantly depending on the project. There are at least 3 different concepts of such disposal sites, depending on their location relative to the Earth's surface. The near-surface disposal site in Novorossiysk was the first one put into operation in Russia. This site is designed to dispose of short-lived and low-active radioactive waste. The disposal site in Novorossiysk is based on the multi-barrier principle. 6 barriers prevent the spread of radionuclides from 3rd and 4th class radioactive waste, mainly overalls, ventilation system filters, and plastics containing uranium isotopes. The first barrier is waste packaging. At first, waste is put in 200-litre metal drums which are placed 4 at a time into special iron casks with a wall thickness of 12 centimeters. That is, the casket body is a second safety barrier. Then we place these casks in our disposal site, and we fill the space between the casks with barrier materials, special clays. This is the third safety barrier. The fourth safety barrier is the 70 centimeter wall for storage itself, made of high quality concrete. The fifth barrier is waterproofing materials which are laid around the site. And the sixth safety barrier is the geological formation in which this disposal site is located. These are the steps that prevent radioactive substances present in the waste from escaping into the environment.
So decommissioning integrators, employees and employees of the companies that are comprised in the structure of this business unit of Rosatom have very broad experience in implementation of really complex, sometimes unique projects on decommissioning, on the radioactive waste management, on rehabilitation of territories. And this also includes, for example, decommissioning of first generation of nuclear facilities and managing of spent fuel, definitely addressing some aspects related to radiation safety issues. And these are all strategically important tasks that are faced by Rosatom. And that helps us to achieve the United Nations goals for sustainable development. And just to mention for us, for 12, definitely that's a business, but it's not just a business because we understand, we fully comprehend that this is also responsibility for us before the next generations. And also, we understand that by making it safely, by providing the best solutions, we also help to substantiate, to ensure that new facilities can be built and that all stakeholders, including public and governments and regulators, will be sure that it can be done safely and that it really worthwhile and can be efficient. And our team, it's a great team and it creates really great environments for working for our employees and even becoming friends, let's say. So that's quite a good motivation for making things better, both on the technical side and on any other aspects. And by this all, we strive to go for direction of the safest, most efficient, economically acceptable approaches for decommissioning projects and radio waste management, and to ensure that in the long run. Dear friends, our presentation is finished, but definitely it's not all of the solutions that we have for this area for decommissioning, for radio waste management and remediation. And we'll be happy to continue this dialogue. You will also see many things in more detail during the coming days in the presentations of our colleagues. And just want to say thank you. Thank you very much for your attention, and we'll be happy to talk more. If perhaps anybody has any questions, or maybe from the virtual audience, we'll try to answer. Yeah.
I just wanted to ask, is the liquid organic waste also treated with the cementation method?
For organic waste, the major concept is that you better bring organics to inorganics, yeah, because that's considered to be the safest way.
Yes, hello. Actually, I have two questions. The first one being, is 12 a R&D component for decommissioning related activities by Rosatom, or is it an industrial?
Also, yes. So as was shown here, but I can tell a little bit more. So the function of integrator for decommissioning, it's not only provision of some existing solutions to the market, but also we have a special department for that to kind of find, recruit, or even order R&D for new products, for new solutions that can either fill some gaps where technologies are not existing or they are not very efficient. So definitely that's one of our areas of competence. And as you have seen here, we didn't have a video because it's really a new technology, but for example, decontamination with ozone, it's one of the new R&D products that we are currently developing, and it's now in the final stages of testing.
And my second question was, what are your career opportunities for international people, if at all?
Career opportunities.
Yeah.
Well, I can address for this matter to my colleagues in HR, yeah, but definitely I think
no, like
we
as
are
in, is Rosatom/12 open to hiring people from different nationalities? Or
I know that's okay, perfect.
Okay.
Yeah, just if in couple of words, for example, we have regional, Rosatom has regional offices in different regions, different countries where I know that local experts are engaged as well.
Thank you for your very interesting presentation. And could you please tell us about what are the commissioning project is implemented by TWEL or your subordinate organization?
There are multiple, let's say, we are in various, in different stages of the project. Some are implemented, for example, in the framework of basic organization of Commonwealth of Independent States. So some projects currently under realization are devoted to remediation and rehabilitation of sites. And many projects are implemented in Russia. So it's basically about decommissioning of nuclear infrastructure. And we also are quite active abroad. So I cannot actually give some full details, but we look at many regions, including Latin America, including Asia, African region. So we try to promote our solutions also there by design, by supply of the equipment, by working out something together, provision and training of personnel. So that's quite an extensive basis for that.
Okay, thank you so much for the presentation. You have convinced me beyond a reasonable doubt about decommission. I want to ask you questions about the turnkey project. Does your turnkey project goes from the construction to design and to the decommissioning, knowing fully well that this long process will take maximum 60 to 70 years? How do you integrate this into the lifelong plan?
I think here is a matter of terms. So I think by saying turnkey projects, we are talking about not the whole life cycle of the facility. Definitely, we also have solutions for that. I will also additionally say about that. But by saying turnkey project and decommissioning, we mean, let's say there is a kind of a circle. If we can imagine that we have some task, for example, so we have to choose the solution, make all different types of like concept design, justifications, calculations. So this is some work on the paper. Then, for example, if we go for a turnkey model, we also design procure production of manufacturing of some components or whole equipment. Then we supply this equipment. We explain or teach the customer how to use it. So train the personnel. We help to license it locally if it's needed. Yeah. So it can be different kind of support both in the metal, let's say, and in the paper by the brains, by necessary paperwork that is needed on both the safety side and also on regulational side and legislational side. And then it's the stage of acceptance tests, for example, some tests use, and then you go ahead with using it. Or otherwise, of course, it's possible to bring our staff also to be with you to supervise you in the works on site, for example. So the customer's personnel can be trained, plus there can be some supervisor just to check that all the process runs smoothly and according to the specification. So,
okay.
And second thing, yes, just referring to your idea about the whole life cycle of the facility, I can just give an example of the approach of Rosatom for turnkey solutions for example, for large-scale MPPs. So, for example, if a country is choosing to go on a step on this road of nuclear energy, and it wants to construct a nuclear power plant, Rosatom offers what we call integrated solution. And this includes all the way from design of the nuclear power plant to helping the customer to choose the type that he wants. The customer wants, design it, manufacture it, sometimes with some parts localized if it's the wish of the customer, and some infrastructure exists. So it's also help with the legislation sometimes. It's help with fuel supply, definitely, contracts for fuel, contracts for red waste management. So that is already included in the in the initial package. So when we prepare the package of the information about the plants, we also include the chapter on how can it be decommissioned in the end. Yeah, so that's for the operator, it would first show that he thinks of that. Yeah, so it's not left somewhere unattended until the next generation arrives. And in the meantime, it also helps to the utility and also to the state to calculate what resources will be needed at that stage, what equipment will be needed, what waste streams will be at that stage, and also the waste streams throughout the whole operation of the plant. So, for example, we have some limits set by the customer saying that you should have maximum these volumes of red waste annually. Yes, and that's the limit. So we have in this way to propose the red waste solutions for the operational stage that will be able to keep it within these limits. Yes, and also definitely that's also part about the waste treatment facility, a waste treatment center, about storages, sometimes solution for final disposal of the waste. It's all developing waste acceptance criteria. It's many things. So it really can be up to these decades of operation, but it all starts in advance in this integrated offer for NPP, where all these things are already included with the best technical solutions that are available as per today.
This is a lot of information. I don't know if you have maybe a video simulation, like simulation, just to make a reminder for students when next, instead of the whole video. It's just an advice, maybe simulation or something like this.
In my mind, I have the slides that we were showing where we have the life cycle of the facility and where it's explained what happens with regards to future decommissioning at each stage and what happens to with regard to waste management at each stage. So what should be considered, what documents are prepared at this stage. Yeah, so for example, like initial decommissioning plan is prepare it already in the early stages, and then you update it, you fill it in with information on operation, on some, hopefully no accidents, but something that happens, and how the plant is operated, because one thing is what we have in design, and then it's live, so definitely sometimes user wants to somehow to modify it, upgrade or whatever. So there is a set of documentation that is like live organism. It goes and getting more and more detailed by the moment when the operator decides to stop the operation, when it's end of life cycle. And by then, of course, we should be ready to have all the possible necessary data. So that's why information management is really important. Yes, to keep all the track records of the operations through the years. Also about waste management. So many things. I think, yes, maybe we can somehow show it through this week another day. I will try to show it to you more schematically, but absolutely that's a very complex, big thing to deal with.
Thank you very much for your presentation. I have one question about contamination in environment. Yeah, this one general or public question. We can find or how many types for to remove contamination if this get in the soil or in the area when we destroy the building after decommission, and which type or which method it is better to remove the contamination if we get or this get
from what type of structures?
Yes, for when you have decommission and destroy the building, transfer some radionuclide inside soil or something about that. How can find which method it's better to remove the
You mean for decontamination of soils?
Yes.
Well, there are various methods for that. I think that's among other things, it's the thing for the operator to decide whether locally it's, for example, whether it's expensive to store the soil. Yeah, so sometimes in some countries it might be easier when storage is available. You just take away some layer of land, contaminated land, like we use here, for example, with Fremes, with this facility for sorting and characterization and sorting. So definitely what you need to see first is how big is this issue? So what is the localization? Yes, if it's a smaller spot, like some hotspots, then it can be just localized, removed with some technique, put into containers or big bags or whatever. And depending on how contaminated is that, it just goes for storage. It's possible to also to decontaminate, and there are various techniques for that. Like, for example, in Bochvar Institute in Moscow, we have several solutions, like to my memory, what I know is hydroseparation, for example. Yeah, so it can just go up, some contamination goes up with some kind of bubbles, or but also it's centrifuge methods that's used to separate on the level of these isotopes that are lighter and heavier and whatever. But it's quite a complex problem to deal with. So it's just first, I think it's needed to decide whether you really want to clean it, the soil, or you want just to take this contaminated layer and send it for the storage, depending on the scale. There are also some approaches, like, for example, what can be done is that the top layer, it can be, I don't know, for example, 15 centimeters, 20 centimeters, up to 30 centimeters maybe. So you can just get it excavated, and then the layer of the lens is turned. So you dig deeper, and then you turn it upside down. So this layer goes down. So that's one of the approaches. Sometimes this contaminated layer of lens, in some practices, as I know, can be taken away and used under when it's slightly contaminated. For example, it can be used in some brownfield areas, some industrial parks, to be used under the this cemented roads. yeah, some underlayer. So it will be not accessible to the people. So it doesn't impose any danger. But these are various approaches. Definitely decontamination techniques exists, but I would say that it's not cheap. So it's really something to decide whether it's really needed.
Thank you so much.
We have a question from our virtual audience, from Laura Knizhnik from Argentina. Hello, Laura. In your opinion, which should be the first steps in R&D departments starting decommissioning projects? So if we are talking about R&D departments, and if we are depending on where is it departments of the operator, is it departments of some governmental utility, or is it departments of some provider of services? Yeah, so that depends. Definitely, first step I would say is to identify where we have some need, where we have a problem, and what do we want to study. Then I would answer the question: are there available solutions? Because sometimes, well, we do not want to reinvent the wheel. Yeah, sometimes we just do not know that the solution exists. So it's good to make some kind of research, or to consult IEA, for example, the experts who are available and really eager to help. Or you can contact the companies that are specialized in the solutions and inquire if the solution is already available. And if not, so if the question is not, and if the country, for example, has its own ambitions to create its own solutions, then we can go ahead with that. So make some research, make some feasibility studies, see what was available perhaps in some weaker versions, like less efficient. So, but first step is definitely to understand the issue and to understand whether indeed there is not yet a solution available. I would say this.
Thanks for this nice presentation. I just want to learn, this MPP construction started, I think, 90 or 100 years ago, and the technology changed so much. At that time, was this decommissioning issues, was it in mind when they are?
It wasn't.
It wasn't, yeah.
It wasn't.
Okay.
I can tell you just out of what I have heard in the conferences, yes, and what is maybe even more known by the cases of research reactors, yeah, because we can see that a lot of research reactors were built before the energy reactors, or some industrial reactors, before the energy reactors were built. And it's really a matter, it's an issue of these old facilities that with the flow of time, they degrade, they are not keeping with the current legislation and tough requirements towards safety, or also because in this case, if it's research reactor, they are testing using whatever materials different, like absolutely crazy, and the conditions of this test and experience are really tough. So definitely it all brings bad effects to the constructions, to core and whatever. So it's a big trouble also because there is no information available about these facilities. And when the time comes, in many cases, as far as I know, also money are not available to decommission that. So what can be done is, again, I believe that it's really a bliss that we have IEA, that helps with sharing this experience. And as far as I know, what is done, for example, is that some missions can be created, and they can help by letting you see the experience in other countries, how it's being realized. Yes, to try to get this experience that you never had. Yeah, because that's the case for most of the countries, I think. Yeah, so these are the major issues, and definitely it's difficult, but it's possible to solve it just trying to get together all the various experience that was through carrying out of such decommissioning projects in some other states. Some are still unique, so like still represent an issue.
So in the future, should we expect new techniques and new models?
Yes, definitely, because when the issues arise, that means that somebody knows that there is a market for that and will be working to provide solutions. And with the flow of time, when companies and providers of services all over the world get this expertise by decommissioning their own sites, as we have, for example, in Kurchatov Institute, it's RFT and MIR reactors. Yeah, it's different with the different channels, like with graphite, and it's pool type, and so it has a really complicated story of operation. So when the project on decommissioning of these two reactors contained in the same building happens, already by that, Rosatom really got a really good experience in decommissioning projects. But also there are other types of reactors, like, for example, some specific, like with sodium, yeah, BR10 reactor in Obninsk, yeah. So the big challenge was, and it's solved successfully, the big challenge was to deal with metallic materials in the core, yeah. So with sodium, with mercury contains also, there was a mercury inside, with this cold traps for oxides, yeah. So each type of the issue that is raised, it gives experience, and then this experience can be shared. Yeah, so this, for example, I think it can be very useful when decommissioning the reactor in Kazakhstan, BM350. Yeah, so I think that it's important to see what is the closest project more or less related to yours, yes, and try to get expertise and help from the people who already dealt with that.
Thank you.
Thank you. Thank you for your very graphic and interactive presentation. I would like to know, according to your experience, how important is to develop this infrastructure and the organization you presented for a nuclear research reactor?
Procedure.
Yes, but for a nuclear research reactor.
Mm-hmm. Well, absolutely. Yeah. I think it's important for all type of reactors, and for research reactors, it's nowadays, I think for any nuclear facility, it's an essential thing. So when it wasn't there in 50s or 60s, yes, when this industry only started, only began, that's because many questions didn't have answer. But now we already have first feedback from this first reactors decommissioned. Actually, if you look at statistics, it's not so much decommissioned in the world, even now. So, and many reactors get to the stage of getting aged, and we can expect a lot of decommissioning projects. And for the safety reasons, all regulators say that, guys, we have to think of that even in the beginning stage, in the planning stage already, to include that. If it's not available, then when you have an aging facility, at any moment right now, it's time to begin to create the initial decommissioning plan, to gather data, all available data, to try to find some team that will be able to get it all together and prepare for decommissioning. Because first, it's safety. It's about safety, but second, also it's about costs. Third, it's about correct planning. So I think that for all stakeholders, and primarily for the operator, it's responsibility, and it's also convenient instrument that helps to manage all the aspects of its utility.
So thank you very much, Yulia.
Thank you. My pleasure.
So we have a coffee break.
Да? Блин. Надо было тебе пересесть. Мне обзвонились.
Hello. I would like just to test if you can hear me.
Hello, hello. Just a minute. Dear colleagues, we are ready to continue.
Dear colleagues, I want to introduce Vladimir Michal, head of decommissioning section in IAA. So, Vladimir, floor is yours.
Thank you. And I hope that you can hear me as very good. Okay, I take it as a yes.
Yeah, just a second.
Yeah, Andrei, can you hear me good?
Perfect. Yeah.
Okay, very good. And I rely on you to move my presentation. Okay. Thank you. So good afternoon or good evening even, ladies and gentlemen. My name is Vladimir Michal. I was acting section head for decommissioning and environmental remediation, but from 1st August, our new section head arrived. So I am not in anymore, at least not permanently. But anyway, I still occupy my original position that is called decommissioning team leader in the same section. And I worked for the agency for about 12 years. So for those years, I was involved in many activities in different countries. And one of the last activity, but that was quite significant, was to organize the IAEA decommissioning conference that was held in May this year here in Vienna, and I would like to provide you with some overview and outcomes. So next slide, please. This is just a little bit view to the history, because you know there were organized different conferences by the IAEA in different countries. So the first one was held in October 2022. And the official title of the conference was a safe decommissioning for nuclear facilities, and it was held in Berlin. You know what is summarized in those points below are always some actions that happened after the conference. So here, because it was formulated as outcomes, as tasks for the IAEA to reflect them. So after Berlin, we started to publish, to prepare and publish multiple safety guides and technical reports on decommissioning of large and small facilities on topics such as planning, costing, and waste management. We also prepared action plan on decommissioning, and there was in place later enhanced coordination, collaboration with EC and OECD MEA. And we also started development of first decommissioning databases and web-based tools. You know, 20 years ago, of course, that many of things that we are now using as business as usual were not available at all. Then 4 years later, there was organized a conference in Athens. I was there only as a participant. The full title was Lessons Learned from the Decommissioning of Nuclear Facilities and the Safe Termination of Nuclear Activities. And there were, again, follow-up suggestions that were widely addressed in new IAEA guidelines and events. There was more promoted and after that more considered something what is called graded approach to decommissioning. So like to have something more simple considerations for smaller facilities and wide considerations for large complicated facilities. And what is more important, there was later on established international decommissioning network in 2007. So it was a more or less consequence of Athens conference. And in 2009, I think, we prepared and we published international structure on decommissioning costing, what is methodology for costing, jointly developed with EC and OECD and EA. And last conference before the one in Vienna was in May 2016 in Madrid. This conference was a little bit different because it was a joint conference for decommissioning and environmental remediation, and as you can see in the title, for global programs. And again, there were new suggestions that were widely addressed in IEA safety guidelines, technical reports, and events. And one of the consequences was that my section was established, and I was also first acting section head, because before we were part of waste technology section as a decommissioning and remediation team, but my team was growing because there was more interest in this topic also after the Fukushima accident. And in 2018, a new section was established. We also more widely promoted young generation. So many of you are also probably in the category of young generation. Once it is a school, summer school. Then we started to have more collaborative projects, development of e-tools, various e-learning, and those kind of things. We started to have more decommissioning peer reviews, also first collaborating centers, and there were also more in practice topics such as accelerated decommissioning, holistic approach to decommissioning, circular economy, sustainability, etc. Next slide, please. I will bother you with some numbers tomorrow during my morning's presentation, but here I would like to demonstrate you just tendency that is in decommissioning of power reactors, and I have the same slide also for research reactor and for fuel facilities. So you can see it those conferences that I mentioned, and in between there is also Fukushima Daiichi accident, and last point is this year conference in May. So in terms of power reactors, you can see that the number of those facilities shut down for decommissioning is growing. It was even a bit accelerated after Fukushima accident because some countries decided for the nuclear phase out. So tendency is clear. However, because of power reactors are like solid facilities, not small facilities, you can see that a number of power reactors decommissioned, it's not so significant. Recently, about like 22, 23 reactors can be considered like fully decommissioned, and but more is growing, so more work is expected for the future. Next slide, please. In the research reactors, you can see that the situation is different. First of all, a number of research reactors shut down for decommissioning is actually decreasing. The first point is that many of them were decommissioned, so like the base for this is lower and lower. That's why it is decreasing, and the number of research reactors decommissioned is increasing significantly because there are smaller machines. It's more easier to decommission them. And so situation is like this. So recently we have 440 research reactors registered as decommissioned. Next slide, please. And for fuel cycle facilities is a situation like somewhere in between research reactors and power reactors. So of course that number of fuel cycle facilities decommissioned is growing, and there are quite a number. But shutdown for decommissioning, they are slightly decreasing because there are many new facilities. And also I have to note that for this chart, I had difficulties to find some historical data from 2002 for research reactors, and for power reactors it was easy, but for fuel cycle facilities not so much. But I think the tendency is clear. Next slide, please. So after Berlin, Athens, and Madrid, there was a decommissioning conference organized in Vienna with the title like Addressing the Past and Ensuring the Future in May. So here you can see website of the conference and the poster. That was quite nice. I personally like, you may agree with me or disagree, that this theme of to have something like a scale of nuclear power plant, but some greening, you know, something what will be returned back to environmental remediation. It is a certainly good idea, and visibly it is nice. Next slide, please. Structure of the conference was very straightforward. We had an opening session with our Director General, Mr. Grossi, and also Belgium Minister of Energy. And President conference was Mrs. Laurence Piketty, who is CEO of Commissariat Énergie Atomique from France. There was session on global status of decommissioning, international cooperation panel, and women in decommissioning site even. For Tuesday, we had the Vice President, Mrs. Marta Žiaková, who is head of Regulatory Authority of Slovak Republic. Main topic was a framework to enable effective nuclear decommissioning. So we had several parallel sessions. We have a special Euratom session with focused on research and development. We have a panel discussion on stakeholders and site repurposing. Also Lithuania / Norway site event, and also event on collaborating centers. On Wednesday, a Vice President was Mr. Brian Wilcox, who is the decommissioning director in Canadian nuclear laboratories. Main topic was managing nuclear decommissioning, and we had a parallel session. And of course, we had also Fukushima Daiichi site event that was quite interesting. On Thursday, we had a Vice President, Mr. Kentaro Funaki, who is one of the research directors in Japan Atomic Energy Institute. Main topic was a technological advancement. And again, we had parallel sessions, panel discussion on supply chain and innovations. And on Friday was quite easy. It was a closing session, young generation panel discussion, Vice President and President final reports. And there were closing remarks by head of my department, Nuclear Energy Department, who is also Deputy Director General, Mr. Mikhail Chudakov. Next slide, please. Well, we originally planned for like conference with 300 participants, but later we had over 400 registered participants. So we had also a number of invited speakers, 69 participating member states. We have 6 international organizations. And on average, we have 350 participants per day, with some of them attending online. And we had over 100 oral presentations. We had the posters, keynote speeches, Vice President and President presentation on Friday. So there was a quite number of talks. And we also had quite a nice number of exhibitions from different organizations, and also booth of my department that provided information about our publications and activities. Next slide, please. We were not lazy before the conference, you know. We specifically worked for some years on the report, Nuclear Energy Series report, that we would like to have published before the conference and provided to participants. And we succeeded. It is this global status of decommissioning of nuclear installations. The report was published in April before the conference, so it was really available. And we also prepared nuclear decommissioning bulletin. Here you can see just screenshot, you know, so those 4 papers are there, but there were much more papers. You can find everything at the IEA website. And we have it also prepared in all 6 IEA official languages. So we have it also in Russian, Spanish, French, Chinese, what is interesting, and even in Arabic, what is even more interesting because it is like, you know, opposite reading. So I also keep it for the future use. So all of this was available during the conference, plus some posters and many other things, visual things. Next slide, please. And now I would like to come into the outcomes that were formulated by Vice President and Presidents in their reports. It is more or less selection, you know, of some outcomes that I consider as important because, you know, we are working on proceedings from the conference. We will have a consultancy meeting on this in September, and I do expect that proceedings might be published next year. And there will be the final formulation because it will need also a little bit, you know, editing and the final touch on English. But ideas will be certainly there. So in the first day, or actually it was the second day, on the framework to enable effective nuclear decommissioning on this topic, there was a highlight from many, you know, presentations. Then there is a need to change the regulatory approaches for decommissioning. My apologies. From prescriptive ones to dynamic and more flexible ones to underway and establish new approaches. And also this supported by visual communication tools taking into account the views of stakeholders. The thing is that as we are approaching the completion of decommissioning, really this regulatory approaches, you know, changes should be considered to support it. Then the next point is about more and more decommissioning projects are reaching their final stages, and guidance on site cleanup and final survey for site release are gaining interest. A release of site with restrictions remains a challenge, and additional clarification of the concept and regulatory guidance are necessary in many countries. For example, in relation to the release criteria and to the definition and implementation of post-decommissioning institutional control. Yeah, also this week we have here technical meeting on you know, measurements and control of environmental remediation sites, and we have there also several guys that are purely interested in decommissioning because they need some kind of guidance after the buildings will be removed on all of the structures, what to do with the land. And next point is that in the current global economical and financial situation, a need was recognized for prudent safekeeping and protection of decommissioning funds, what may be really an issue in some countries. Next slide, please. Then the main challenge for advancement of decommissioning project in many countries is still a lack of disposal facilities for radioactive waste and plans for disposal. Yes, because we have countries with the decommissioning program for many years ongoing, but without any disposal capacity. But fortunately, we have also other examples. The practices show that countries with clearly defined radioactive waste management policies facilitate their decommissioning activities more effectively. Continuous efforts are necessary to advance the establishment of national policies and strategy for decommissioning and waste management, including aspects of waste disposal. Another point is on aging, you know, of the nuclear facilities worldwide, and the increase of the number of decommissioning projects require continuous efforts on competence development in many countries. This effort would benefit greatly from enhanced international cooperation. And then we have a point that conference recognized and welcomed the progress of several international research and innovation projects related to waste management and decommissioning, and emphasize the needs and benefits of the research and innovation activities, in particular those related to characterization, dismantling technologies, and waste management. Next slide, please. On managing nuclear decommissioning, I trust I have only one slide that stated that the integration between decommissioning and waste management continues to be the most important partnership to ensure optimal management of waste arisings and avoidance of repacking or multiple handling, or even like creation of potential new legacy situations, legacy sites. Optimization is an important trend in decommissioning to deliver work on both large and small projects more effectively, making best use of resources. The fleet approach to build once and deploy several times was presented by several countries and organizations. And the last point here is that decommissioning teams are adopting new technology, especially visualization tools, to improve collaboration and planning. The use of digital twin models is making the work safer and more efficient, especially to assist in material handling, mock trials, and to guide workers in the field of to avoid hazards. Next slide, please. And I have two on technological advances because it was a large topic and there were many good things presented. So first point is that the application of advanced technologies in the decommissioning process in enhancing efficiency and effectiveness in all stages. Planning with digital tools leads to enhancing the physical walkdowns and reducing the time. And also digital tools for smart planning are bringing new options for more optimal and accurate planning and preparing of activities. Second point here is that the application of advanced technologies in small nuclear facilities and research reactors is an opportunity to implement activities in small scale and later to develop into full-scale applications in nuclear power plant and other large nuclear facilities, such as fuel cycle facilities, for example. Capturing the lessons learned and updating the systems with the new emerging technologies is necessary along the full decommissioning process. So it is more about knowledge management and lessons learned and knowledge management. The development in the field of robotics and remotely operated tools is an advanced stage in many countries. The sharing and international cooperation is necessary to accelerate the development and applications in the nuclear field. Looking to other types of industries to gain from the applications of advanced technologies brings the benefit in usage of proven and workable technology. For example, we established very good cooperation with European Demolition Association that can really provide a lot of about the good technologies. Next slide, please. Cost-benefit analysis is driving the decision process for deployment of the advanced technology into the project. The higher cost for the technology development in first sight may impact the implementation if correct cost-benefit analysis is not performed. The increased initial costs are often worth in price as optimization of the waste production or human effort is significantly decreased. It is certainly true. So to invest more in the beginning means to save more during the implementation. Despite significant amount of remotely operated and digital tools for mapping and displaying of radiological conditions available on the market, the implementation in large scale is not that common. Development of tools for radiological characterization of building and materials is still underway. Yeah. Training of personnel using extended or virtual reality is under development in many countries, while application of the tools was so far not yet commonly used and expensive. International cooperation on this topic would be beneficial for the accelerated implementation. And last point here is that remotely operated technologies are largely used in different sites. the collaborative approach on sharing the technologies for the same type and also different types of reactors may be beneficial. And there are really such a good examples already, but we can build on this and to have more. And I think that last slide is just with pictures. Next slide, please. Yes, so it is like the concluding slide, but I include there pictures of my director and the conference president. You know, one picture from exhibitions, one picture from the reception, and one picture from the concluding young generation panel with different young people provide their perspective on working nuclear decommissioning field. And it concludes my presentation. I think that there is still time for some questions if you wish.
Thank you very much, Vladimir, for this such interesting presentation, interesting review. Dear colleagues, maybe you have some questions. Yulia? No? No? Okay. So no questions. Thank you very much.
You can keep your questions for tomorrow because I will have some presentations in the morning. So let's have it in the morning. Yeah.
Okay. Thank you.
Thank you. Thank you so much.